Okay.
There you go. There you go.
Oh,
Oh, yes. Thank you for tuning in, everybody. We are so happy and excited to have Bill Gate here and Christopher O'Neill here. We are just continuing this, like the round two. Bill Gate has a fantastic presentation of his new physics about the Roth hypothesis. And we are going to have a lot more debate. So we start with, first of all, an opening statement from Christopher for about 5 to 15 minutes, followed by opening state from Bill Gates, another 5 to 15 minutes, and then give an open forum. We start debating, and then we ask questions, and then as we go along, Christopher is also there. I am just moderating for the first part, but then they get on to that, and it's not totally controlled or anything, but I just moderate in case I had to, clarify something or I want clarifications and things like that. But mostly it will be, we are all together in this, so we'll be continuing.
Yeah.
So let me give the floor to Christopher to get going with his opening statement. Thank you.
Okay, great. Thanks, Rajan. So, yeah, so just to clarify, we could do like 15-minute opening statements, but it could be short as like 1 or 2 minutes. It doesn't really matter, I guess. But and then I thought we'd do like like 5-minute sections, but so like for rebuttals, yeah, 2 of those, and then maybe open dialogue. But yeah, we'll see how it goes. So okay, I got to share a screen. But actually, I suppose Rajan, yeah, you're the moderator, so you get to decide how it goes.
Okay.
Because you're the one who has to time everything.
Okay.
So right, hide that. Okay. So can you see that?
yeah.
Yes.
Okay. Let's start from the beginning. Oh, there we go. Okay, so I've produced a couple of slides here just to help clarify some of the points that I made earlier in the last time we met up, because I wasn't really thinking about having to defend like my own theories on anything, so I kind of forgot. I started developing this one a bit more, so we'll get into it. So the kind of topics or objectives that we're going to look at is surface tension gravity as calibrated by GPS time dilation, and then we'll look at some classical tests such as light deflection, Shapiro delay, Mercury's perihelion shift, gravitational lensing, and rotation curves as it applies to dark matter. And then we'll take a look at a unified field theory using surface tension gravity. So that's unifying gravity, the electromagnetic field, the weak force, and the strong force. And then finally, we'll just look over the hyperspheric universe model, because that also came up in the last talk that we had. So usually we start with some related work, because there's not a whole lot done on surface tension as it relates to gravity. One of the big ones would be by Himanshu from 2013. And that was using surface tension to describe tangential pressure of a normal curvature in curved spacetime. Then Callaway, much earlier, did sort of the opposite thing, where he looked at the density matrix of black hole entropy as a means of studying surface tension in fluids. Further related work would be from Bartholin and Barbara from 2022. And that is kind of closer to what we're talking about today, where they modeled a visible universe as a 3D surface of a 4D universe that is essentially filled with a heavy fluid. So we're going to take a similar approach, but we won't have, it's not a 4D model in this case, although there is 4D considerations when we go up to the hyperspheric universe model. It also has this theory also has similarities with the Sage's theory of gravitation, which we spoke about the last time. We were trying to remember, who the details about this. And so the basic idea is that gravity is the result of all of these corpuscles that are going around. And basically, if you have an isolated object like A, it'll be struck equally from all sides, resulting in no directional force. But if we put in a second object, it will shield. They'll both shield each other. So there's less corpuscles in this region. So the push happens from the outside. So let's look at surface tension gravity. So first we'll look at surface tension pressure. So here we just see a diagram of surface tension. You have a model in a molecule in the bulk, and it's pulled on all directions. Yeah, and so this, but at the top, there's a disparate, like it's asymmetric, so it causes this the surface to pull to a minimum area, and it's defined by this. So surface tension is equal to the force divided by the length, where the length is the base of the container. And but so in our model, we're going to have a push for. We're going to model it as a push force, and so it's a similar idea. It's just when you have a surface here where the matter would be, there's an asymmetry, so it compresses towards the matter object. Okay, so here's surface tension gravity calibrated by GPS time dilation. Using a compression profile and calibration, we arrive also using the mass of the Earth, that's our test mass, and the GPS altitude. We get, for the compression profile, it's a very small number, but we also have the pressure that we would experience like at sea level, I believe, with the Earth. So that's 6.18 times 10 to the 9 pascals, which is interesting because it's close to the compression of water as well, which is around 10 to the 11 or 10 to the 10. Here's some just some data about the absolute pressure at sea level, the orbit of the ISS, and the orbit of GPS, which is much higher. So we see that the pressure goes down. Likewise, the compression. So here's we're interested in the surface tension. So you remember we had force times length before. So the length in this case will be the circumference of the Earth. And so we get, for surface tension, we get quite a large number, and that's in newtons per meters. And then we can work out the force from that, which is also a fairly large number in newtons. Here's just another diagram showing the same thing, the model pressure as a function of altitude. And we see sea level, the ISS, and then GPS way down there. So here's the classical test results. We see that for the light deflection, for Eddington's experiment, it gives 1.753, which is very close to the 1.75 arc second benchmark. So that's quite a good result. Same with the Shapiro time delay, we got 233, was that picoseconds or something, and which is close to the 200 and the 200 value that we're looking for. And then we have Mercury perihelion advance. We get that bang on. So the reason why this might be so accurate is because it essentially uses the same sort of metric theory and equivalence principle as general relativity does, but the equations are different, obviously, because of it's a surface tension gravity model, and also the equivalence principle sort of falls out of it. But there's different ways of working out the metric theory. You could have a variable speed of light concept, or you could have like time speeding up at closer to a gravitational field, to a massive body. So and then that could cause time to then slow down in order for the speed of light to remain constant. But then that could have contradictory knock-on effects elsewhere, for example, in special relativity. So that needs to be looked into. Alternatively, you could just model all of general relativity as a force, because they usually say gravity is not a force, it's a geometry. But here we would have gravity as surface tension, so which is a force, obviously. And naturally enough, if we wanted to explain gravitational lensing through surface tension, it would be an obvious fit because of the refractive index of a curved liquid. And you can kind of see that there. It even looks like that. Excuse me. Now, as for galactic rotation curves, which we know to be sort of flat as we go out, this was an unexpected result from both Newtonian gravity and Einstein's general relativity theory. So they had to fix this problem, they had to come up with a new concept, which is dark matter, and that allows the whole galaxy to rotate as a unit. But you can do this experiment yourself if you make a cup of hot chocolate and stir it up, and there's bubbles on top. Once you stir the liquid around, you'll see that they all rotate in unison perfectly. And so we can see an explanation for why that is the case here. So, for example, in tea, which is a bit like the cocoa or hot chocolate version that I mentioned, the bubbles move towards the center of the cup due to centrifugal effect created by the stirring. And crucially, this increases the pressure on the outside and decreases it at the center. So, it offsets the perfectly offsets this sort of lag time that we might expect on the exterior. But you won't see that in coffee so much, but that's because the bubbles are slightly different. They're smaller, volatile compounds. Okay, so here's the unified field theory. I won't go into this in great detail or anything, but basically you can, because we're modeling gravity as surface tension, we have this thing called the Cheerios effect, and that relates to electrostatic pressure as well. So we could generate like a kind of a 4-vector with so we have +1 means attraction, -1 means a repulsion. So if we have a field, let's say these are two negative fields, that in electrostatics that will be a repulsion. Same with two positive fields, but these will attract. But then it's flipped on its head then for gravity, because two negative like gravity fields that we normally see will attract. Two anti-gravity fields would also attract, but the opposites would repel. So that gives us the electrostatic vector then would be this one, as mentioned, and the gravity one, surface tension gravity, would be this one. So we can kind of think of those as two limits or ideal vectors, and then rotate between them smoothly. So that's kind of what this is showing. We have electrostatics here, capillary gravity here, and then just using an SO4 rotation through the 4th dimension, we can flip those two, so we can create a mixing value and therefore unify the two vectors. And that's, so then in this case, we attempt to unify all of that structure with the strong force. And the way we do that is we just combine the EM vector and the G vector together using this equation. And then so that covers that. That'll be the SU3 vector then, 8-dimensional. Then we can also just extend the electrostatics to full Maxwell's equations, quantize the field to get the photon, and then treat that as the electroweak field after symmetry breaking, so that you kind of unifies with electroweak symmetry breaking. So the entire Lagrangian then is L EM plus the surface tension gravity plus the QCD plus the electroweak symmetry breaking. And there's just the Lagrangian for the quantum, the SU3 structure constants. So, wrong directions. You can also go further and posit that maybe there is a type of dark matter which is more like oil, because we said that space is a lot like water. We could have, so it has a surface tension of 4.1 10 to the 7 newtons per meter. Then if we imagine dark matter is like a different kind of space instead of matter, it would have the surface tension could be different for this kind of space. So it'd be closer to that of oil, which is around half that of water. And then we could imagine an even stranger kind of space called surfactant space. And that would, if introduced, it would cause the end of the universe through an effect called the Marangoni-Gibbs effect. Just quickly then to cover the hyperspheric universe model so we know what we're talking about. We have a 3D stereographic projection of a sphere onto a tangent plane, but it would be like a 4-dimensional hypersphere onto a 3-dimensional tangent space. And this kind of answers the question as to whether the universe is finite or infinite. The plane is infinite, but the sphere is finite. And then we can map the galaxies onto the sphere, obviously, project from the 4D sphere into 3-dimensional space, and that works well. It also, because of the anamorphic perspective from the sphere onto the tangent place, we get stretching effects, which could be linked to redshift. And other people have spoken about this, including I think Arthur Pletchard, and if I'm getting his name right, I might have blanked on that, and Unzicker as well. So the conclusion is surface tension gravity. It passes the classical tests, explains gravitational lensing, explains galactic rotation curves without the need for dark matter, and unifies EM, gravity, the electroweak, and strong forces, the weak and strong forces. So the question is, can the rope model do all of these things? So that would be standard tests. And then there's the references. So, okay, Bill.
Thank you, Christopher.
Thanks very much.
So I think you kept about 15 minutes,
just a bit over, maybe?
That's fine. Yeah, a little bit, but it's okay.
Sorry
I just want to inform everybody that Christopher just now passed his Viva, so he'll be Dr. Christopher O'Neill. Congratulations.
Yes. Thanks very much.
The same way. Yeah. So he'll be doctor.
To do the corrections. I don't know if that makes me a doctor yet, but
yeah. But next year you'll be graduating sometime. The new year. So that's good. I'm Rajan Iyer. Now let me introduce Bill Gade. If we can, I was not completely sure, Bill Gade, you were physics, right? You what's your major in? Your major?
Engineering. I'm in engineering.
You are a doctor of engineering, master?
Yeah.
You're a doctor of engineering, right?
Yeah, but the issue is we speak a different language with Chris. What he said. He's talking in Klingon, and I what's his name? Carl Sagan said, "Who speaks for Earth? I speak for Earth."
Okay, fair enough.
Okay.
Yeah. So we talk a different language, okay? You raised so many issues. I don't think we'll be able to cover all of them today in any depth. Yeah. All I can say is give you a general feel of where I stand. Okay. And of course, when people listen to me, they get shocked because nobody has heard any of what I have to say, ever. And so it's like, Galileo coming up with a new theory, and the priest saying, "What are you talking about, Galileo?" That sort of thing. The issue is as follows, okay? This is as I understand physics, as I understand science, okay? First of all, mathematics has nothing to do with physics. Mathematics has nothing to do with science. Math is not the language of physics or of science. We don't use mathematics at all. Okay, that's the first one. And I know you'll beat me up. Give me a chance here, okay? I say mathematics has nothing to do with physics. Second, we don't do experiments in science. We don't do experiments in science. We don't do experiments in physics, okay? Why? Why both? Math can only describe. And I'm saying that science is about explaining. Here we are 10,000 years later. No one on planet Earth, other than us, because we do have a physical interpretation, no one on Earth other than the rope model has a physical interpretation for why this falls downwards always, right? And I'm saying there's only one way to figure that out, and that is you have to identify the invisible, intangible, that is invisible, intangible objects that are pulling on this downwards towards the earth, okay? Now, Chris mentioned that there's something pushing, and I got a problem with push because, you know, we push from every side, but the question is if the particles are pushing from outside to this thing, then where are those particles coming from? Are they coming from Mercury, from Mars, from Venus? Are those particles coming out of Venus? Does gravity work in reverse over there? Are they being pushed out? Because, I mean, you know, if the particles are pushing here from above, from the sky or from wherever, they're coming from somewhere. And that's something, that somewhere, that something is losing particles. They're sending them to us. So I have a problem with the push gravity, any kind of push gravity, shadow, Lesage mechanisms. That's one issue. So we're not going to detect that through an experiment, and we're not going to be able to explain it with math. Math can only describe. Math is a descriptive language. It can only describe. It cannot tell us what exists or not only what exists, you know, out there, but how it works. Okay, it can tell you what the visible stuff works. Like, you know, you can tell me something about this because you can see it and touch it. You can measure its speed, how high it came, from what height it fell, all that kind of stuff. You can measure and come up with equations and descriptions for how the rubber band came down. The only issue is, you know, you haven't told me what it is, what physical object is pushing, pulling, or whatever on this, right? That's the issue. And I'm saying that for 10,000 years, we never figured out the only thing that we had to figure out. And that is that when this falls, okay, there is a pull force. That's what most people say is gravity. I agree with that part. I'm saying it's a pull force. And there's something that is invisible and intangible that is connected to every atom of this rubber band, to every atom on Earth. So when this falls, it's because every single atom of this rubber band is connected to every single atom on Earth with something that is invisible and intangible. We cannot see or touch this thing. It's a thing. Why is it a thing? Is it because we can see or touch it? No, it's a thing because it has shape, but no object, not all objects can be seen or touched. And that's where the problem is. I think that was the secret we had to discover of Mother Nature, that there are things that cannot be seen or touched, and we cannot see a table on the other side of the universe. Does that mean a table, the word table, doesn't represent a physical object? Hopefully a table here or there is a physical object everywhere, but it's not something you can see or touch. I cannot see the air. It's made out of atoms. Hopefully it's a physical object. Anything made out of atoms should be a physical object. The fact that we have a chair or a table that is solid and the air, which is not solid, water, which is not solid, does not mean that water and air are not physical objects. Of course they are. And they are physical objects because they're finite. You know, there's you get a bunch of air or you get a bunch of water, you put it in a balloon, you take it out into space, you pop the balloon, there's a blob that comes out. That blob has shape, right? That blob has shape. There's a finite point for the whole blob. And so that blob has shape. Now, does it change shape from moment to moment? Yeah. We're not talking about changing shape. We're saying, does it have shape? And the answer is yes. It has to be a yes. On the other hand, there are concepts. and concepts don't have shape. You know, love does not have shape. Intelligence doesn't have shape. Energy doesn't have shape because we don't know what energy is. Mass doesn't have shape. These are mathematical concepts. So we cannot use mathematical concepts in lieu of physical objects, meaning that, you know, which is the first criterion we have for irrationality. If you move a concept, you have an irrational theory. Okay, we can only move objects, and physics first and foremost requires an object, and no textbook on earth of physics ever defined what an object is. Begins by defining what an object is, and that's where we failed. If you don't define what an object is, nobody knows what an object is and thinks that an object is that which you can see or touch. Of course, when this comes down, then people say, well, I can't see or touch anything here, so there's nothing there. No, it's not that there's nothing there. It's that you cannot see or touch that something. That was the key issue. And so what we're saying is that all atoms in the universe are physically interconnected. They're connected by a DNA-like rope. In fact, we're saying that DNA got its idea from the rope model of light. In other words, that's why we have DNA also in this format. And this explains just about everything. Explains first the speed of light, why it's a constant speed. It cannot be otherwise. Little c, 300,000 kilometers per second, is equal to frequency times wavelength, meaning that if you raise the frequency, you must lower the wavelength and vice versa. And under the rope model, it's very simple. You torque the rope, you have more links, and each link is shorter. If you untorque the rope, the links get longer and you have fewer links. Frequency times wavelength. That's why the speed of light is a constant. That's the first issue. The second issue is that if we were to unravel every rope and every atom in the universe that is made of the same thread, we would end up with this. We would end up with a rubber band, a very thin, extremely unimaginably long, closed loop thread, meaning like a rubber band. And we're saying that that's what matter is. It's the single thread that little by little formed all the, not because there was a process. I'm just saying that that's what we have out there. We have all atoms interconnected, and the atoms are made of the same thread as the rope that interconnects them. And it's a single piece if we were to look at all the atoms in the universe. So our model is totally different than what Chris explained. Nothing in common. We don't think there are discrete particles. There's no such thing as a ball. All atoms are physically interconnected. That means from this ball, we have all these gazillions, and I mean gazillions, gatrillions, gazillions of ropes sticking out of here. And those gazillions of ropes make up the atom, which is connected to another atom. If I can find the other ball here. We have one ball connected to the other ball, and there's a rope-like mechanism or entity like this interconnecting them. That's essentially our model. That's our basic model. So it's a totally different model than what people have heard out there. And all I can do is tell you what the theory is and how to explain light, gravity, especially electricity, magnetism, and the atom, how it's built and how it works. You know, the quantum jump, for example, and that sort of thing. So we are able to explain all these processes with this model, but it's totally different what you find out there. We're saying that quantum mechanics, general relativity, string theory are not part of science. They are irrational theories because they move concepts, they move mass, they work with field. Field is a bunch of numbers, a value at each point in space. They move vectors, numbers again. All particles in the standard model, they're all numbers. There's not a single one that is a ball. They treat it as a ball in all their physical interpretations, but when you put them against the wall, they say it's not a ball. And so what is it? Well, it's a wave. It's everywhere. It's here. It's there. It can be at two places at once. It can go faster than light. So they have all these contradictions out there, and I'm saying that all that is irrational as a physical interpretation. Okay, so we cannot use that in physics. And there you see, okay, there you have the model. Essentially, you have the wave, the transverse wave that was created by people like Fresnel and Maxwell and so on. And the problem there is that what is a wave? You see all those arrows there, and those arrows are vectors. That's what you're staring at. So you're staring at numbers. They're magnitudes, right? And then you have all these vectors, and they form two fields. What are fields? Well, fields, there you have the definition of field, a value at each point in space. Field is just a bunch of numbers. So all you're staring at something that they represented pictorially with arrows. What you're really staring at is, a mathematical concept, and you cannot move concepts in physics. Hopefully, the universe doesn't work with a movement of concepts invented by us. And what we are saying is that what Father Universe, Mother Nature out there, what God, the devil, all of them out there, what they have is really a rope that we cannot see or touch, again, smell or hear, right? You cannot detect this through the senses. You can only use the common sense, the visualization, and say, look, could it be that all atoms are physically interconnected? And if they are, that's a good model that you see there, because you can see, first of all, it matches pretty well the electromagnetic wave that they've been mathematizing all these years. That's the first one. Second, it does have this wavy structure. And instead of a one-way, as you can see on the right-hand side there, instead of a one-way travel of all these vectors, which are just numbers, we have a torsion, an in situ torsion of the rope, and it's a torsion. That torsion is what we call light. In other words, propagation along, you can say propagation of a signal, of a disturbance along the rope from atom to atom. And now we have, again, a physical model, because the atoms at the end are also made out of that same thread. So the whole universe is interconnected. That's our bottom line. It's all interconnected. And now, because they are interconnected, we can explain gravity. And I have a couple of videos there, quick videos that I could put on just to show you, illustrate for you how gravity works. You know, so a picture is worth 1,000 words. A movie is worth 1,000,000 words. So I can show you that if I have a way of giving you a link that you can just quickly pass by. They're all very short vids. So
okay, Bill. If you want to message me in the chat, I guess
I can do it here. Okay, let's try it here. I'm going to give you a link. Okay, let's see if this works. With a plus sign.
Oh, well, the plus sign with the screen would be, you would be able to share it yourself from your computer.
Oh, no. How can I pass you a link? That's the question.
Yeah, if you go to the right-hand side of the screen, there's something called private chat, or you could just stick it in the main chat.
Oh, I see. Private chat with everyone in the studio, that one?
Yeah, that could work.
Let's see if I can put it in there.
So it's a YouTube.
Can you put that one on, or do I have to click it?
No, I can get that.
Okay, if you put that on, you'll get an idea of gravity, of our explanation for gravity. Just one picture shows you, the whole thing.
Okay.
It's about 15 minutes, but you can continue, I think.
Okay. Sure.
Can you put that on there?
Yes. I'm just trying to figure out which thing to load. I guess entire screen. And then this is it, I think.
Yeah, there you go. So here you have a spoon falling to the ground. Why does it fall to the ground? Well, it falls to the ground because every atom that makes it, you got to redo it. Every atom that comprises the spoon is connected to every atom on Earth. So what happens? As the spoon gets closer to the center of the ground, the ropes fan out. You have more and more ropes intervening in this action. That's why you have the acceleration of gravity. And at the extreme distance, like, at infinity, all the ropes come together and form a single coaxial. That's why gravity is weak. Gravity is strong the closer two objects are together, consistent with Newton's equation. So this is the mass divided by distance square illustration of that. What was missing is the ropes. People could not see and touch them, and so they said there's nothing there. And we're saying, yes, there is something there that you cannot see or touch. Okay?
Yeah.
So that's the model. I have another one for for an astronaut, but essentially is the same thing that you saw there, an astronaut falling to Earth. But the same thing. What we're saying is the ropes fan out. As the object gets closer to another, mass closer to mass, distance square is reduced. What you have is the fanning out of the ropes that interconnect every atom.
Okay.
So it's not a push mechanism, it's a pull mechanism. Okay.
Pulling each other. Okay. So is that it, Dr. Bill Gates? You have some more, or
I don't know. I mean, I could go on forever. You asked the wrong guy, because here's two magnets. Okay, I always show those fridge magnets, and you can see that they stick together. And the question is, how do we explain this magic? And what I'm saying is, hopefully here there's something that we cannot see or touch. They call it a field. And but a field is not a physical object. What was a field? A value at each point in space. That's a mathematical concept that says if I measure here in this region, I'm going to get a value, a different strength. Okay, that's a field, but that doesn't tell me what physical object is bringing these two things together. And hopefully this is not a push mechanism. Okay, hopefully this is not a push mechanism. When you have it here, you can see it's already pulling from the inside. Okay. And the force is on the inside. It's not on the outside. My hands are not being pushed from the outside. I can feel it pull from the inside. Okay, that's what I want to show there. And so the question is, how does this work? Well, the threads, very simple. What you have is gazillions of threads. When they're going in the same direction, in opposite directions, one clockwise, the other one counterclockwise, right? If you got this situation, they push each other away. They spin around at great speeds, and they're hitting against each other like paddles of a riverboat, going in opposite directions. And so they hit each other and push each other away. And if they're going in the same direction, when these threads, gazillions of threads come down and gazillions of threads come up, you have the attraction mechanism. Okay, now you have attraction. So repulsion and attraction. And that measures perfectly the lines of force that Michael Faraday discovered in the 1830s perfectly well. You get a magnet, and what you get is these curves. And what those curves are, those lines of force, are really sweeping of threads through the iron filings, going through the center of the magnet and coming back out. Can we see or touch them? No. We cannot run an experiment. We cannot go to the field or the lab and say, I'm going to run an experiment to detect. No, this is something you cannot see or touch. Therefore, no experiment is going to elucidate what is in that world we call field. You can only visualize it, imagine it, and explain using that model. That's all you can do. And again, we have the same situation for electricity. We have the same thing for the atom, gravity, etc. The whole works. Light.
Okay. So thank you very much, Dr. Bill Gates. Excellent presentation.
Thank you.
Now the forum is open. I think the debate is open.
Okay.
And Christopher, you can.
Do I get a 5-minute rebuttal to that or something?
Yeah. 5 minutes.
It's kind of open forum anyway, but I just want to respond to a few things in one go.
Okay.
So so the first issue there was to unmute myself. So to respond to the first one of the first points Bill made about
the principles were no math, no experiments.
Oh yes, yeah. Okay, well, we could start there, I guess. You mentioned something about math being just descriptive. I think that's a valid point, but I think
that's a what point?
A valid point.
Oh, okay.
By the way, I got 5 minutes here, Bill. But I
didn't understand the word. I'm sorry.
No problem. Okay, so yes, it's descriptive, but if you have a very powerful description that could be used to explain something in the long term, sort of. So, for instance, if you think of Newton's gravity, where he kind of unified the forces of heaven with the forces of the earth, and through his descriptive mathematical equations, it wound up being an explanation for orbits and how planets move around the sun and the earth. So, or moons move around the earth or the moon. So, yeah. So just going back then to so you mentioned you wanted to know where the molecules are coming from. Now, my theory is like a fluid model, which is the medium, and the fluid is kind of space. Like there is no difference between what we think of space and what we think of this fluid substance. The space is exerting a force, and that force is on every point in the universe, so throughout the universe. But if you introduce a massive body, then that blocks off the fluid, because the fact that the matter is there, the space is not there. So then there's this pressure differential where, and that will force anything here, like a smaller object, towards the bigger object, or two equally sized objects. Doesn't really matter. So it's not Lesage's push gravity, where these corpuscle molecules have to come from somewhere. Well, actually, I think he's saying that they just come from space as well. I'm not sure, but I'm not promoting his theory of like particles bombarding a surface or anything like that. So they don't come from Mars or anything. They are literally a property of space. Space is a volume. It's some sort of bulk, and that has a force. And we can even see that in things like maybe the Casimir force. You know, when you bring something very close together, you get a force, even though it's just an empty space. So imagine what it would be like if we're talking about all of space. Surely, you know, if something that small can produce some sort of force, then you can imagine that the entire universe would also exert a force. So yeah, so I noticed you didn't explain how the rope model explains things like the weak force or the strong force. You might have a way of explaining those away, like, and that's perfectly valid. But yeah, but also I'm not saying that electromagnetism is a pull force, because remember I say that gravity has like one 4-vector polarity, and then electrostatics or electromagnetism has another one which is completely opposite to it. So, and they're connected by this gauge symmetry with the SO4 rotation, and then that produces an inverse. So if anything, it would be a pull force in that sense, just as it is described. Now, you mentioned speed of light as a constant, and I think that's fairly well accepted. But I've also noticed that well accepted. Oh, it's well accepted. Yeah, within physics and science in general. But you also mentioned, not here, but in other videos, that space-time curvature, this sort of fishnet idea, is erroneous. So, but space-time curvature is about the contraction of space and the dilation of time. And I'm just wondering, how do you keep, you know, like a bookkeeping mechanism, if you like, on the constant of speed of light when you're traveling fast or close to a gravitational object, if you like, without invoking space contraction and length dilation. So I'd be interested to hear about that. Yeah, there was some other points you made about a medium, like that I would have to cough up like what my space is made out of. It would have to be some sort of material like water or air or something, and these have to be made out of molecules. But you know, you're positing this rope model idea, but surely, and that's your medium, but surely you would have to be sort of stricken to the same standards whereby you know, what are the ropes made out of? Are they made out of nylon or plant material? Surely they'd have to have some sort of physical substance as well. But if they don't, and there's still a medium, then, you know, I think the same could possibly hold true for the space medium that I'm talking about. Although we do note that it does have properties, like it has a surface tension and a pressure value, which could be close to water, where we could make it exactly water. So it's kind of interesting from like a biblical point of view, which, you know, is like, how do we know? Are the waters above the earth and the waters on the earth or below the earth? Yeah. So you get what I'm talking about there. So it kind of works from that point of view as well. Yeah, I suppose the final points, I don't know how I'm doing on time here, but if you have like
few more, one more minute you have.
Oh, okay. Yeah, I'm not really sure how this connects to the points you were making, but there is the idea, like, if you have two large objects with the same volume, but one is very dense and the other is less dense, they will be they'll both experience the same sort of pressure from from space because of their surface area is the same, and then all right. So this is the principle of equivalence, effectively. But if you had a smaller object that was more dense, it would have it would have fewer lines connecting to it, but the object, because the object's more dense, there's more shielding inside than like a larger, less dense object, which still has more space. So there's less of an imbalance. So then those two things, I'm arguing, cancel each other out completely, and you could have the equivalence principle from that. But most of the equations I use just tie it directly to mass, so you can apparently do it that way as well. But I'm not really sure if that really connects to anything you're saying. I'm just clarifying something. Okay.
Thank you, Chris. So you have about 5-minute response, Bill.
Yeah, I know. The problem is he raised a million issues there.
Oh, yeah.
It's very hard to cover all of them. Let's see if we can cover some of the main ones. Maybe we can clarify some points here. The first one, I think, is, well, two things. The first one is, what is an object? And the second one is, what is space? And apparently Chris believes that, or he makes the assumption that space is something that is made out of something that it's some medium. And we're saying it's not. There's no such thing as space. All we have is objects. The objects are what we say in space, but they're not really in, because space is not a container. Like when you put apples inside a box or whatever, a pail or whatever, then you can say the pail or the box is a container. Space is nothing like that. Space is neither finite nor infinite, because it's a concept. Space is the same thing as the word nothing. What is nothing? What is space? What is vacuum? That which has no shape. It's a concept. And so concepts don't have shape. They don't have size. They're not finite or infinite. Only objects can be finite. Okay, so we start from that point. Space is nothing. What is nothing? That which has no shape. What is an object? That which has shape. So we have nothing, which has no shape, and something which has shape. And so now they're antonyms. Now we can use the word consistently in a conversation. Okay, and I think that's where the main problem is. Chris is using space as an ocean. He's saying it's this ocean that it's applying pressure from outside inwards towards objects. Say anything that falls on Earth from the sky downwards, it's being pushed from the outside, essentially. And the Earth blocks the push from the other side, essentially. I think that's his model in general. But then again, that's a problem, because Mercury has the same thing. And where are the particles coming from? Where's the medium that is compressing coming from? Space cannot push in every opposite direction at the same time. Why is it pushing against the center of Mercury, against the center of Mars, and against the center of the Earth, when all those are different directions? I mean, what gives those particles directions to go, in opposite directions? Why? That's one objection I have. What's the other objection? The main objection, and that is that space has been measured to have 10 to the minus 12 torr. There's one particle every so often per meter cubed. So there's nothing there. I mean, compared to Earth. Earth, you have tons of particles per meter cubed, and out there in space you got 10 to the minus 12, which is approximately what they've measured on the moon, which is approximately what they measured in the solar wind. So there's no air there. There are no atoms in space. Space is not a medium. There are things there. Again, I say it's the robe, and I say there are particles like atoms and ions and so on, but there's very, very few of those. There's not enough material there to push on anything. When the astronaut goes out there, he's not being pushed by all these particles that, push us down to Earth. When I let go of this ball, it falls, right? And because it's immediately, it's instantaneous, you know, there's an instant push there. And that's not happening to the astronaut. And he's in space. Why isn't he pushed around by these particles in space that make up space, the medium? So I'm saying no, space is not a medium. Space is almost completely empty, except that it's got, you know, particles and, again, all these ropes that are crisscrossing from every atom in the universe. And that's your cosmic background radiation, the ropes that are out there vibrating and sending light, etc., that we cannot see or touch. That's why, you know, we're connected to the moon. The moon, every atom in the moon is connected to us. Every atom of us is connected to the sun. And we cannot see those connections. You know, and so the sun curls the earth around like this. Okay. Why? Because that there is something there. There is something uniting the earth to the sun. And I'm saying those are gazillions of ropes from every atom of the sun to every atom on earth. Close to the earth, you have a bird's beak, right? Because, you know, the ropes are going up and going down and going in and going everywhere. But as you get farther away, you get this situation. Okay, you get a situation where you have all the ropes in a single coaxial, essentially. So this is what's happening. That's the reason the Earth goes around the sun, because it's tied to the sun. And the same reason that the moon is bound to the Earth, and the moon swings, the Earth swings the moon around in the same way. And that's happening. So it's like the epicycles that Ptolemy had, but it's not just with abstract concepts. There's a physical object, and it's the gazillions of ropes that interconnect every atom from one object to every atom of another object. That's the mechanism we're proposing. So one issue is, again, space. We're saying it's completely empty because we define it as that which has no shape. So it's not a physical object. It's the opposite of what an object is, which is that which has shape. And so we have something, which is that which has shape, and nothing, that which doesn't have shape. We can use the words consistently now in a dissertation. That's the first issue. Second issue, you raised quite a few issues there. You talked about, you know, the ropes. The ropes, I think it's very easy to understand. If every atom in the universe, you know, here you have an atom, that's what we say it looks like. It's a shell. It's a membrane, a physical membrane that encapsulates a star. Think of a rolled up porcupine or rolled up sea urchin, right? With all the points, you know, pointing or sticking out radially, right? That's what's inside. And it's a shell. It's a ball of yarn kind of surface, right? That encapsulates this star that's in there. What is it made out of? It's made out of every rope coming from every atom in the universe that converges on our atom. That's our model. He said, what is the rope made of? Very easy, 2 threads. So the real question is, what is the thread made of? That's what people want to know. They say, what is the rope made of? Rope is easy, 2 threads. There it is, two twined threads. So it's no biggie. No, the question is, what is the thread made out of, right? And I'm saying it's a single closed loop thread that looks like the rubber band. Oh, here it is. Hold it. That looks like this. Okay, closed loop thread. That's makes up all the matter in the universe, right? And we're talking about something unimaginably thin, unimaginably long. So if we were to unravel every atom, every rope in the universe, that's what we would end up with. It's made out of a single piece. It is flexible. Those are the assumptions we make, right? And so you cannot cut it. You can cut something that is made of pieces, of parts. You cannot cut the thread because it's not made of parts. It's made of a single piece, but it has the properties that make up water, gas, solids, etc. Why? Because it has all those properties. It's made out of a single piece, but it's flexible, okay? And usually we think that something which is made out of a single piece is rigid. What other question? I don't know, because you raised the
I did mention that. I did say a few other things. I think I asked about the speed of light being a constant. How's that possible?
What do you want to know about the speed of light being a constant? In fact, I think I've got it here. I think you got it in that, what is it? the chart I sent you, the pickup I sent you. Could you
Yeah.
put that up one more time? Because
Sure.
it's easier to explain when you have this picture in front of you. All we have to do is point to the picture, and it's much easier to explain. Picture's worth 1,000 words.
It's definitely related. So
sure.
Okay, so I want you to see something. You have the little c equals the frequency times wavelength. That's the F and the lambda, okay? So that's the equation of a rope. There's no other object that can simulate that equation. There is nothing you can imagine that can simulate that. Why? Because what you're seeing there is that, again, if you have a rope, right, and I'll put it close by, the more you torque it, the higher the frequency, in other words, meaning the more links you have, the shorter each link is. Wavelength goes down. If you increase the wavelength gets longer, you have fewer links for the same amount of rope. So that is the equation of a rope. There's nothing else that can simulate that equation. And because of that, the speed of light has to be a constant. It has to be like that little c there, 300,000 kilometers per second, rounding off, right? Why? Because, again, all we're changing is the number of links and their link length, as we call it, depending on whether you have longer wavelength and shorter wavelength, or link length, as we call it. That's all we're doing. This is what the rope is doing, just going like this and going like that. That's it. And torsion is the fastest thing imaginable. It's much faster than any wave. Again, that's a wave. That's a mathematical concept that you see at the top there. But why is the speed of light so fast? And I'm telling you, it's fast because the fastest thing you can imagine, is a torsion wave. You know, there's nothing faster than a torsion wave. And that's why it's the speed limit of the universe. So it's not only a constant, but it's the speed limit. Both. It explains the swiftness of light. You cannot explain that with a transverse wave because, and here's an example for you, for you to compare. When there's an earthquake, you have all these both longitudinal and transverse wave moving across the ground. It turns out that the longitudinal waves sound, you know, longitude back and forth,
that transverse,
one-dimensional. They're 1.7 times faster, 1.7 times faster than the transverse wave that move because they have to go up and down, right? These go back and forth, the longitudinal ones, and the other ones that go up and down travel 1.7 times slower than the longitudinal waves. And the torsion wave leaves both, you know, in the dust, you know, biting the dust. Torsion wave is the fastest thing that you can imagine. There's nothing faster that you can imagine. I mean, I challenge anyone to give me a mechanism that is faster than a torsion wave. Why? Because it's already connected at the other end. You know, how do they explain, for example, in college, right? When you're in college, they explain the, the standing wave. And what do? They do this. They move it up and down, okay? But see, the only way you can maintain this straight and at the same time send a signal is through torsion. It's got to be connected at the other end because watch what happens when I let go from the other end. So you know, it better be connected at the other end. Otherwise, you know, why does the wave, the transverse wave, go straight? Why do they always paint it straight? Why does it just fall like this? You know, why does it do that? So the transverse wave is a bad model. Even if it were a physical object, it's not. But assuming it were a physical object, you would not be able to explain straightness by having it go in one direction. The torsion moves in both directions simultaneously. That's why I can see you and you can see me at the same time, faster, you know, as fast as light. It's not because little photons are going from my image to you, to your eye, and image from your physical bodies to my eyes. That's not what's happening. We're connected. We're physically connected right now. Okay. But, and then, so I guess the other question, I think that, I don't know if it was direct or indirectly in there, but let me answer that. You know, when you take beads on an abacus and you slide them, right? You slide beads on an abacus, you don't take the wire with you. You know, the bead slides along the abacus. You can slide it over. It doesn't pull on the wire through which it passes. Think of it that way. That's the mechanism for the rope. What you have is this. You have the rope. You have an atom, which is my fist, right? And what it's doing, it's eating into the rope because it's made out of the same two threads. One thread goes through the top and forms the electron shell, the electron membrane, and the other one goes through the center and forms the proton, what we call the proton star. It's a star in the center. So the star is made out of threads, and the electron shell is weaved by threads as well. But as soon as you get to the edge of our atom, you have the rope connected to another atom, which has the same structure, and so on down the line throughout the whole universe. So the reason, an object can move without pulling on the rope is because it slides through the rope as it eats into the rope, and the rope, one thread goes around, the other one goes through. And so it's sliding like a bead on an abacus. So it doesn't pull on the wire.
So let me ask for a clarification. Okay.
Yeah.
So the fiber you are talking is not an object. Is it? It's not an object. You are saying the string or the rope is not an object.
What do you mean the extreme?
The rope. The rope is not a object.
Well, the rope ends in an atom, and one thread of the rope turns into the encapsulates. In other words, think of gazillions of threads encapsulating, forming a ball of yarn that encapsulates a star, what we call the proton star. We have the proton with all its threads because it's made out of single threads, right? And so you have this star in the center encapsulated by a surface that you can imagine as a ball of yarn because it's a wavy surface.
So the thread or whatever is not like a silkworm that pulls the thread and connects to the other one. It's not like a silkworm thread. It's not formed from the.
Remember, everything is under tension in the universe. Every atom is the ropes are under tension always. Ropes never bend. They're always straight. Not straight. The word is not straight. The word is tension. They're always tense. Okay. And the tension is given by the speed of light. That's why the tension's always constant. All you can do is increase the frequency, the number of links at the expense of wavelength, So if you increase the number of links, you're going to get shorter wavelength and vice versa. Okay. The longer the wavelength, the fewer links you get. All you can do is just change that. That's the frequency times wavelength. But what the atom is doing, hydrogen, we're just going to talk simple here. Hydrogen atom is just expanding and contracting. That's the quantum jump. When it does so, it twists the rope and it sends the torsion to the other atom. Okay, so all we have is torsions going from atom to atom. Why? Because all the atoms are pumping at great speeds, quantum jump between energy levels, between orbitals, right? So it's not a little bead like in quantum mechanics that's jumping back and forth between orbitals. What we have is something that's pumping back and forth. That's why they say the electron is everywhere. Of course it's everywhere because it's a shell. It's a membrane that's encapsulating the atom. And now you can explain gravity because every atom is connected. As one object made out of gazillions of atoms approaches another one's, the ropes fan out as the objects approach each other. So we can explain gravity, light with the same mechanism, with the same model, in other words, right? With the same rope, because everything is physically interconnected.
See, one problem is that what is the rope made of? The
rope is, once again, the rope is made out of two threads. We got it. Next question.
But what is that a material or is it?
No, that's why we have to get the language straight. You go into quantum mechanics and you say, what is this particle made out of? And they say, well, give me $1 billion. I'll build a collider, right? Atom smasher or particle smasher. I'll smash it. I'll tell you what the electron is made out of. Okay, and what is that electron? What are we going to call that? Let's call it a Peter. Okay, so now we have a Peter. What is the Peter made out of? And they say, well, it's an elementary particle. What do you mean by that? Well, it's an elementary particle because it's not made of anything. Okay, and you're saying, well, hold it. So that's the ultimate particle? And they say, no, give me another $1 billion. I'll build another atom smasher as big as the solar system or as big as the galaxy. And I'm going to smash all the Peters. And then what is it made of? It's made out of Johnnies now. Okay, so we have all the Johnnies. What is that made of? And where does it end? So the problem they have is a question of language. If we were to go with the particle notion of the universe, that everything is made out of discrete particles. All those particles have to be made of more particles, which are made of more particles, which are made of more particles. Where does it end? Is there an ultimate particle that makes up all the particles in the universe? And of course, quantum predicts that. It's logical that you cannot, cut the onion, peel the onion and get to nothing. No, there's got to be something at the final end. So as much as you want to break up any particle of quantum, you're always going to end up with more particles, but at some point you end up with one particle. It's a conceptual issue. That's the only one you can call an elementary or fundamental particle. What's the situation with the rope model? The rope model is there's a single thread in the entire universe. If I can find my, I lost my.
Wait, yeah.
Whatever. Anyways, you saw the rubber band, right?
Yeah.
It's a rubber. If we were to untangle everything, we would end up with a rubber band. Okay, a single, very thin, extremely unimaginably long, closed loop thread. What is the thread made of? That's the question. What we call the single thread or the universal thread. What is that made out of? It's not made of anything. It is the ultimate. That is an elementary or fundamental particle, thing, object, whatever you want to call it. That's the ultimate. It's not made of anything. It's made out of a single piece, and it makes up everything else. Now we know the definition of the word elementary particle or fundamental particle, because we do have one, but quantum doesn't have one. They say, just give me more money, I'll break it up, and I'll tell you what it's made out of.
Okay. So I think I get 5 minutes. That was a good question, though, Rajan, because that was exactly the question that I wanted answered previously.
Okay.
So I think we got an answer for that. There's a couple of other things, though, because I think some of your pushback against my ideas, I kind of already explained them previously, but I'll try again. So for a start, the pressure, as I said, it's not particles coming from space. So
then what is it? Then what is it?
But it is like space itself. I mean, you're talking about like what is it made of? It could be, you could say like space is a fundamental object then, and that it has
but what is an object then? Tell me what an object is.
Well, no, but I'm saying you're saying the rope is this fundamental medium that isn't a thing. So I could just use the same definition then for space, couldn't I?
No, but hold it, Chris. This is the issue. You need to understand the question that I have. The question is, I'm saying an object is that which has shape. If you have a different definition, that's fine. But if we go with that definition, what is the shape of space? What does it look like? Does it have shape?
Oh, okay, yeah, I'll get into that. I still technically 5 minutes to go, but all right. So because so I'm gonna stick to that. So yeah, okay, I'll loop back around to that. Yeah, there was a couple of other things though that kind of confused me. It's not so right. So the point is, how is it pushing? Like, how can it push on the Earth? How can it push on Mercury and Mars all at the same time, because they're all in different directions? But that goes back to the image I showed, where you have a point and there's lines of force pushing from every direction, and that's happening at every point in the universe. So unless, of course, there's an object blocking part of so there's a point here. There's lines of force acting on all sides except the side where the object is. So it blocks that out, and then that creates the force. So it's perfectly valid that the force can be moving in this direction towards Mars, this direction towards Mercury, and this direction towards Earth, because it is an omnidirectional force. So and it's
being depleted for somewhere.
What?
I mean, if something goes towards the center of the Earth, something goes towards the center of Mars and other planets and other stars, etc.
Yeah.
Where is it coming? Where is it losing? Where is it losing pressure?
Well, you see, that's the point. So you have the object. I was going to explain that. So you have the object, and so that's shielding the force that should be coming from this side. So in a sense, what the force is being generated by the object. The simple fact that the object is present reveals the force that is already there. But if the object is not there and the space is empty, then the force is hidden by its own self-cancellation process. So
you know what would help, Chris, if you can make a little video with that image, a GIF or whatever, where you have, the forces moving towards the objects, several objects, and showing how the forces are moving, whatever pressure you have there, particles or whatever you have, how that's working, in all directions.
But there's no particles. But I mean, it's simple enough. Like even this picture here that I was just scribbling, it
Yeah, but see, that doesn't explain it, not to me at least. I would like to see a video of that, because I need to know what the source of that pressure is and how it blocks at the same time that it sends space.
Oh no, so the point is that the pressure is like, if you just have empty space, then the pressure is there, but you can't sense it because it's all self-canceling, because it's omnidirectional. So it's the same force this direction as it is this direction. This direction.
Okay, that I can understand close to the Earth, but there's gazillions of much more space than there are planets or matter, for that matter. And so the question is, if you have a planet here, another one far away, and so on, you got a lot of space there. Are you saying that it's the space that's creating the pressure? And if it is, it's taking away from the pressure that I need to do the same thing at Mars and the sun and whatever.
Okay, well, I think there must be a slight confusion here, because when I was talking about the cancellation part, that would only happen in like free space where there's no gravitational fields. But close to the Earth, the pressure differential is going to be affected by the surface of the Earth, which cuts out some of the lines of force from this side, thus making the lines of force of this side actually have an effect.
Again, it would help a lot if you make a little video of several objects, several celestial objects, tiny ones, being pushed by whatever, because I don't know what this material is. Again, you're saying space is made out of something. And if it's made out of something, it's a physical object. And if it's a physical object,
not necessarily. Not necessarily. But for instance, it could be like a sort of representation. So I'll just continue on. So you made a couple of other points. Do I still get some time to rebut here, or are we in open dialogue? It seems like we're in open dialogue at this point, isn't it?
Yeah, open dialogue. Actually, I can give 1 minute, 1 minute each. That makes it, to explain 1 minute for you. And that
open dialogue just means there's no there. Yeah. Okay. So, all right, Bill, let's do that. So, yeah. So basically, I'm saying that because with the surface tension gravity model, if it was just that, I would understand that you'd be making the point could hit home more. But because I've got this as space is an object, the hypersphere is an object. So, and that is made of a liquid, is a bubble, and then it's projected onto a sheet or like a three-dimensional space.
What's outside of space, giving it shape?
Well, the space is just flat, like a flat plane that kind of goes to infinity. So then you have it's a flat surface, but it's actually three-dimensional.
You're saying it's 2D, not 3D?
No, it is three-dimensional because the sphere is 4D.
And so is it 2D, 3D, 4D?
Well, so if you look at the image that I showed with the sphere sitting on a flat plane, that was just to demonstrate the idea. But obviously, it would have to be up one dimension because we perceive the universe along the plane. We don't see it as a curved sphere. So when they measure space and they say, oh, space is flat or whatever, then so this is basically the same thing. They're saying like space is three-dimensional, but it doesn't have curvature in a sense. So, and they say
we went from the flat Earth to the flat universe. Yeah.
Yes. But I'm bringing back the round universe as well. So, and so there we go. So we've got
the issue I'm going to pinch on, I'm going to throw acid on that wound is I need a picture of space. And when I get a picture of space, I need to know, whether it's a sphere, a flat plane, whatever, I need to know what gives it shape. What's on the outside of that?
Well,
because otherwise it wouldn't have shape.
Well, yeah, hang on a sec. It's a good entire screen, is it? Well, it has shape because it is a shape.
Yeah, like, but in order to conceptualize shape, you need to find something on the outside of it. Like there, you have some white, there you have some white stuff on the outside of the flat one and the round one. What is the white stuff? That's what I want to know. I don't want to know what the blue stuff is or the flat one. I want to know what the white stuff is that gives it shape.
Right, but we're already so if you think about it, this is the universe. We're at the center there somewhere.
Okay, what's the black stuff?
These are all the galaxies, the blue things, and then space.
What's the black stuff?
Well, that's what we call space, Bill.
Okay, but you're saying that space is a thing. What's on the outside of that black stuff?
Right. So this black stuff here, then in this representation, is the gray plane.
Okay, then what's the white stuff? I want to know what the ultimate one is. I don't care about the other stuff. I care about the white stuff.
Right, but you have to understand this is just a representation. This gray sheet here goes to infinity. And then
no, there's no such thing as infinity. Infinity, there's no object that is infinite. Infinite is an irrational term.
Well, that's actually
all objects are finite, and infinite is an adjective. You can only use it with objects, and there is no object that is infinite. That's why the word infinite is an irrational term. It belongs in math for numbers, but it cannot be brought into physics.
Well, that's interesting, Bill, that you should say that, because this is what we're looking at here is a 3D stereographic projection. But what we notice is we have the sphere, yes, which we both agree in this sense is I would call it a 3D object. I know that mathematicians like to refer to it as 2D because it's some sort of manifold, but I don't agree with that necessarily. I think it's confusing and a bit of a waste of time. But the point is that from a mathematical point of view, at the top of this sphere, we have something called a projection point. And that point, because of the way the maths work, projects to infinity. So technically, this point here, which is like 0, 0, 0, 1, which is X, Y, Z, W, essentially. Oh, no. Well, this would just be X, Y, Z because it's 3 dimensions. That point, the projective point, is not in the set down here. All the other points are, but this one, because it goes to infinity, is outside the set. So you're correct. Infinity is not part of the universe.
That's physics. It's math.
The incessant counting up to the infinity is valid. So it's the same thing that you're talking about, essentially. Now, if you ask what the substance is around this, well, you have to...
the white stuff.
No, not the white stuff, because the white stuff is... Well, okay, let's call it that then. But
that's the one I need. I need the white stuff. I don't care about the visible stuff. I want the white stuff that gives shape.
Yeah, but like the area that you're interested in is in front of the sphere here, yeah, and above all of this, and it's not white. It's clearly clear because we can see through it. So that's why I'm saying
that's like the used car salesman trying to show me the door when I want to see the trunk. I want to see the trunk of the car. No, let me show you the door. I don't want to see the door. I want to see the trunk. I don't care about the blue stuff. I don't care about the gray stuff. I want to know the white stuff that gives shape to everything.
Basically, the space around this cylinder, yeah, is what you're interested in.
Because I can see the cylinder. Why? Because it's got shape. It's got shape because there's a contrast.
Yes. So you want to know about it. This would be an infinite what's block around the cylinder. And so my answer to that is, so we know what this is roughly. The gray part, because that's space. We're looking at it all the time. We know
what space. The gray part is space, you're saying?
Yes, like this.
Okay, right. I want to know what the white stuff is, or the black stuff in the other picture.
Yes.
What gives shape to space? Because if space is a physical object, a medium, an ocean, whatever you want to call it, then it's got to have shape. It's got to have something on the outside.
Right. So right. The sphere here has a shape, and that's caused because it is a bubble. So it has.
Well, it's not because it's a bubble, because there's got some white stuff giving it contrast. That's why it's a sphere. Otherwise, the sphere would be infinite. It'd be a single block of whatever.
Well, I don't know about that, but it's a bubble because it's two-sided. So there's like space inside the bubble and there's space outside the bubble. So there's some sort of pressure going on, presumably. But the point is that I'm trying to make is that when we live we know about the 3D space because we live there. We can infer a lot about the hypersphere because all of the same information that exists here exists there, just mapped through stereographic projection. But what is difficult to talk about is anything beyond that yet, because this is it's pretty much a new field of I'd say it's about maybe 10 years old, or less. So we're still studying that. I have some ideas, but it must be some sort of gas or something, I would imagine. But then you could say, well, what's that? It doesn't really matter at that point, because we already have a medium. We can call it. We could say whether it could be fundamental, but like your fundamental object has gravity attached to it. It has electromagnetism, so it can be all these different things, even though it's fundamental, which I'm not so sure about. But you have to give me some chance to push back on some of the other issues. Oh yeah, so we asked what is the substance. I'm not entirely sure. I'm certain on that.
So we gotta wait. We gotta wait for another conference where you can clarify for me two things. One is what gives shape to that, and the other one is the question I had with what was it earlier? I think to show me the mechanism in motion. In other words, show me a bunch of balls, we'll call them stars, planets, whatever you want to put in there, but very tiny, because you've got a lot of space and very little matter. So we're going to have all these planets surrounded by a lot of space, and I want to see the mechanism also of how they press only against within, towards the center of each one of those objects, and where is all that force coming from? Whatever pressure,
Well, yeah, actually, but there was one other point that I didn't really make properly, I think, or maybe. So if you go down, so this is another way of describing the same thing that I'm talking about, the surface tension.
That's a soccer ball.
Yes, sort of. It's what is it? It's a pentagonal tessellation of the Poincare disk. So essentially, this is a hyperbolic space. But the interesting thing here is we can see at the center, we have 5 lines converging on a single point, and they're all the same length. Yes. So that's like, if we imagine those lines as lines of force, then that they're all canceling each other out. Essentially, you could have like an infinite number of lines if you like. Yeah. We can do that. Okay, but then if we get to this point out here, we see closer to the edge, which is this boundary. So the white stuff out here is like a physical object. It's some sort of material, and what's in here is space. And so this point here, the lines are shorter this side, but longer this side. So we can imagine more force pushing this side, less force this side. So you kind of you get closer and closer to the boundary. You speed up because of gravity. And so
what's pushing? Particles?
What?
What's the material that creates? You can't use the word force. Force is a concept. I need to know what physical object is intervening there. You put arrows, that's fine. That's the direction of the force. Yeah. What is the medium, the thing that is pushing, that is arrowing?
The point that I'm trying to make is that this is just right. So the model we have is a surface tension gravity model. So we have a force and a length, which would be the circumference here, and then and we have a surface tension, and all of that is explained through a kind of a force model, yes, because of the pressure of space.
Yeah, but force is a concept. You can't use the word force and say force is a physical interpretation, a theory for the mechanism. Force is a mathematical concept. The question is, what physical object, physics, is pushing there?
Well, yeah, but we have that through the surface tension gravity model. But I'm just showing you a different kind of model, which is very similar. So this is like, as you get closer to the edge here, you're going to get more. Basically, this is what I'm saying is this is a good analogy for the surface tension model, where we have the pressure from all sides, but over here the pressure is less because we're getting closer to this boundary. And then as we get to the limit, there'll be zero. These will become much longer than these, which will go to 0, and then you'll have total contact. So the point is that this model is called anti-de Sitter space, I believe.
And
Yeah, so you can use this.
But the issue I have with anti-de Sitter space is that the question is what's outside of him. I want to know what the white stuff is, and if possible, the blue stuff that encapsulates the white stuff. I'm concerned always on the outside. You know, before we can understand this, we need to know we need to identify the objects.
Well,
and
I already
if you're saying that red thing, that red football there. If that's a physical object, then I need to know what the white stuff is that gives shape to that physical object.
No,
because if space is on the inside, the white stuff cannot be space.
It's not space. This is space. This is space. This is a physical object out here. We've kind of inverted space. So this is infinite space out here, and this is the Earth. The white stuff is the Earth that's been inverted, like turned inside out.
Okay, yeah, but then
clarify something.
No, there's a point I'm trying to make here. There is a point I'm trying to make. So we agree with that anti-de Sitter space. This is well-known stuff. But like if you think about it, these are all like ropes, aren't they, Bill? So basically, this is another rope model that I can.
If it's a rope model, why don't you put ropes? Why did you put lines of force, arrows of force?
Well, yeah, but you know, you could have them as ropes, or. But what I'm saying is that your model is contained within my model. It's like a submodel of my model.
Yeah, but your model ends up, because I don't understand this inverted thing that you're saying that the Earth is upside, inside out, and you have space on the inside. That's so realistic for me. Our universe hopefully is very simple, very, very simple. We've made it complicated because of math. It's math when we use words such as mass, time, energy, force. Then we get into trouble because now we're dealing with concepts instead of dealing with physical objects. Hopefully Father Universe and Mother Nature, they work with physical objects, not with concepts. They don't know anything about energy and force and mass and time. In fact, there is no such thing as time, as I say, that's for another day. But the issue here is they work with objects. Hopefully everything is done with objects, and some of them invisible and intangible. And that's all I can think of. But other than that, we cannot just describe and say, oh, the force moves inwards. Here's the little arrow that points in that direction. And the arrow is bigger, meaning that it's stronger than the shorter arrow. Those are all descriptions. I need a physical mechanism, a physical picture, or a picture of the physical things that are intervening in this process.
Well, I just said it's an analogy for the other system, which is a physical process, which is well understood and can be graphically displayed. So I think from that point of view, it's okay. I think maybe it's not a direct comparison with your work, but it's not a million miles away either. I mean, I suppose when you have the idea that with the spoon, it's falling to the earth. And then the ropes fan out. So I suppose I could ask, because you're asking fairly tough questions of my of everything here. So I have a similar.
Can you interrupt 1 minute? Can you interrupt 1 minute, please?
Wait a second, Rajan. Okay. I'm just gonna. Okay. Right. So if something is moving towards the Earth, then it is easy to see that the ropes will fan out, and the fanning out produces the force known as gravity, which will further pull the object, causing a feedback loop of sort of, to whatever. So accelerating the object until impact. I think there's a terminal velocity that has to do with air. And stuff.
But important there, Chris, important to keep in mind something else. Why gravity is instantaneous and not like mathematicians say that it takes 8 minutes for gravity to come to the Earth. If the sun were to disappear, we wouldn't know for 8 minutes. That's nonsense. And I'll tell you why. Obviously, we can destroy that thought completely. And I'll tell you why. Yeah. If an astronaut is out there in space, okay, and he's a few miles away from the Earth, right? He has a certain weight at a given location, at a given distance with respect to the center of the Earth, given by Newton's equation, which is amply verified, okay? Now that astronaut takes 1 inch, moves 1 inch closer to the Earth, his weight already changed. He's got a totally different weight than he had one millimeter away. All he has to do is change his location, a static concept, and his weight changed instantaneously. He's got a different weight. How do we explain that?
Yeah, that's kind of the point that I'm getting to here, or it's a little bit connected. So we talk about this kind of feedback loop, accelerating the object until impact. Okay, but if the object is not moving to begin with, like let's say it's at a limit, like the ideal limit like it's totally in free space, right? Everything is attracting it at the same amount. All right, so it's not moving to begin with then, and but what would cause then the fanning out of the ropes in the first place in that instance, or would it just stay there? Or conversely, since the ropes should always be fanning out to some degree, like if it moves a slight bit, like you said, then it's slightly closer to something else with a bit of force. So it's going to, like, it might take millions of years, but eventually it will start moving towards that object. So the question I have is, since they would always be fanning out in that sense in one direction to some degree, what is stopping the object from inexorably accelerating in this direction despite it initially being at rest? Or is that...
Well, yeah. Remember, you have any object. Take the moon, our moon, right? It's not only being pulled by the Earth, it's being pulled by the sun, by Jupiter. Everybody pulls on the moon because all atoms are physically interconnected. That's what we're saying. That's the model, okay? But Jupiter is very far away. The sun is even farther away, okay? So the moon is affected by them, but you can imagine that all the ropes connecting every atom on the moon to every atom on Jupiter, as big as Jupiter is, as big as the sun is, they're far away, and so they're all, all together. They form a single coaxial. So the effect of the sun and Jupiter on the moon is much less than the Earth, which is much closer. That's the only issue. Now, what happens? You can imagine the moon, at a certain distance from the Earth, okay? And so in between, you have this coaxial. As you approach if the moon were to approach the Earth, let's just say along the connections that they have, these ropes, if it were to fall towards Earth, all those ropes, as the moon comes closer, it gets bigger and bigger. Its diameter is much more noticeable. That means that the atoms are now farther apart. And so the ropes are fanning out simply because of the distance that is decreasing between the two objects. And so, the model is straightforward. It explains Newton's equation completely. The only reason Newton wasn't able to explain it, he was thinking of particles, and he said, well, I don't see any particles, so what's causing this? So he could not figure that out. And I'm saying the answer to Newton's equation is ropes. If you had ropes, now you can understand it because you can visualize the mechanism.
Yeah. So that was thanks for that, Bill. So I don't know, Rajan, did you want to go?
Yeah.
Did you have something?
Yeah. So the white space they are talking about could be a de-Sitter. So the difference is a de-Sitter space when it inverts becomes anti-de-Sitter space. Could that be a possibility of explaining that white stuff or the space?
Well, no, the white stuff should be a gravitational thing. So that circle you see, that's like kind of they usually have it as like one slice. So then they build that up as like a cylinder, and so you could have projections from the surface, I think, into the bulk space, and that's supposed to be like, talking about moving in a gravitational field versus so they're sort of linking special relativity motion on the surface of the cylinder with motion in the curved space within that. So really, that's all that's showing. The hyperbolic tessellation grid thing in the center shows a curved space. Presumably, since the curvature gets more intense towards the edge, that means the edge is some sort of physical body. So it's like this circle. You can imagine this circle is the Earth, and all around it is space, but then just invert the whole picture and you'll get Earth around the outside and space in the center. Very easy to do if you've got like a four-dimensional sphere. Like I said, all you need to do is rotate the sphere. But you could even do it with that 3D sphere sitting on the two-dimensional plane. Let's say the bottom half of the sphere is black and the top half is white. When we project that onto the surface, the tangent surface, you're just going to get a big black. I said black on the bottom, yeah. So you're going to just get a big black circle all around the sphere, and then a white circle outside. But if I rotate that sphere 180 degrees in the x direction, x or y or x direction, then now the white part's on the bottom. And now what you're going to see from the point of view of someone looking at it, the black circle in the center is going to start to grow. Then it'll become like a flat line. So now all of this space down here is black. All of this is up here is white. And then it just, as the sphere continues to rotate, the projection will make this close up again. And the black part will sink. And the white part, which was infinite before, and all around the circle in the beginning, will now be enclosed and become the white circle. And so that's what we're looking at. We're looking at a Poincare disk, if I'm saying his name right. That is the space, the white space, and the black space, which we are saying is a physical body like a planet, can be inverted from being a black circle to now an infinite black circle around us. Does that make sense? Do you know, actually, the Germans believe that
it's so realistic. But let me just say, Chris, the only two questions, homework for you, if you care to take them, is again, I need to find out what encapsulates space, what's outside of space, what gives shape to space if space is a physical object, and I'm defining as a physical object or an object as that which has shape. So it has to have some contrast. And then the other issue, in other words, I need to identify each one of the objects inside my picture, whatever picture you present. That's one issue. The other issue is you're saying there's this pressure, okay, that gravity is some kind of pressure, like here on Earth, the pressure is coming from outside. There's a push on me rather than a pull, which I think you can prove to yourself cannot be, because I can stretch my arm, right? And I don't feel it pushing. I feel pulling. It's the Earth pulling from below and not something pushing from above. But
yeah, fair. Well, I mean, I suppose,
but this is my point. If you're going to illustrate that you can illustrate your idea, in other words, you have all these planets or whatever little balls, show me how it can push inwards to each one of those objects. And where is that force coming from? You're saying it's coming from the space itself, but somewhere it's got to be depleted if it's going towards the planets.
No, not necessarily. Yeah, so that's a weird thing.
Yeah, that's the part I'm not understanding.
I haven't been able to communicate that for some reason to you, but I suppose
because you can communicate it very easily by making a video. Well, because that's true. A video is worth a million words.
You could think of, like, with the bubble, like with the surface tension model. Oh yeah, hang on a sec. Yeah,
but again, we need it for many objects.
So with the surface tension model, as I showed you, it's defined as not the gravity model. I just mean the surface tension of a liquid. It's described as a pull force. So we could actually redo the whole thing as a pull force. That was a mistake on my part. I got confused between push gravity and surface tension. So I kind of mixed the two up there, muddled it up a bit. So I'm going to have to, I might look into doing it as a pull force rather than a push force. That's no problem. The question I have for you then, Bill, is how is it, right? So like I said, my model unifies gravity, magnetism, the weak field and the strong force, and electromagnetism, whereas yours ignores the weak force and the strong force.
Completely. There's no such thing.
Right, yeah, fair enough. But then you'd still have to the
weak force, the gluon, the strong force, all that is just mathematics.
Right, but then
it's mathematics. That's all it is. Yeah, they had to explain why a neutron converts to a proton and how a proton converts to a neutron. And so they introduced this notion of quarks, and they said, well, an up quark turns into a down quark, and then you have the proton converts into a neutron, vice versa. So it's just mathematics. There is no such thing as a strong force because there's only two forms that we can imagine: push and pull. There's no maybe. Okay, but these people created push, pull, maybe, and perhaps. They have four forces. What is that?
Well,
what is the one? It's a pull force. What is the weak force? It's a push force. So there's still two forces: push and pull. There's no other force.
Okay, but so you do agree that there are these two forces then?
Right.
They're just
okay. No other forces.
Something they have a model for beta decay. I don't think the rope model has that. So you would need to.
We don't need it. No, we have a model for beta decay. Yeah, I do have that. I have it illustrated, you know, but I mean, it would take too long to explain. All I'm saying is, even though you have beta decay, there is no other thing than push and pull. So I don't know why they invented these 4 horses of the apocalypse, as I call them. They're not 4 forces; they're 4 horses.
Yeah, no. If you got a model for that with your, that's good.
Yeah, I've got a model for beta decay.
Yeah. You have to show us that. Maybe you could either come back here or on your own.
Well, I have lots of videos out there, you know. So I put all this in images so people can watch and they understand the mechanism that I'm proposing. Doesn't mean you have to believe it. All I'm saying is you have an interpretation that you can take to the bank. You can say, okay, I understand it. Whether you believe it or not is a separate issue.
Oh, that's fair. So well, the last thing though that I think, you know, well, there's the flat rotation curves is modeled using my model.
You mean for dark matter or for what?
Yeah, but we don't use dark matter. We just have the curvature and the rotation. But we also have the what's the gravitational lensing? How does your model with ropes come up with gravitational lensing?
Very easy, very easy. Like let's go back to Arthur Eddington, 1919. You heard of that, right? He's the guy who supposedly proved Einstein through gravitational lensing. How do we explain that? You have a star behind the sun, okay? Yeah. You have an eclipse, and somehow they were able to take a picture of this star that's behind the sun, and they say, oh, okay, so light curved around the sun and reached our eyes or reached our camera. And baloney. Baloney for several reasons. If light is a photon, we cannot talk about curved space. We're saying that the photon deflected, not that it was bent, the photon itself. You know, the road is what was curved, but you cannot say that we bent light. No, you can't bend light because if light is a photon, a little particle, you did not bend the particle. You can say that you deflected the particle. That's the correct language, but they don't use that language. They say we bent light. Okay, that's one issue. But how do we explain it? Very simple. Every atom of that star is connected to every atom in the corona of the sun. Okay, so every atom that forms a corona is connected to that star. And it relays because our model functions through relaying. The ropes don't go anywhere. They're already connected. So all you're doing is sending signals through the ropes. So imagine gazillions of ropes of that star behind the sun connected to the corona of the sun, and those same atoms stimulating and relaying that same signal to our eyes. Okay, and or to the camera. That's what's happening. So we don't have to bend light. It's done all with straight lines, with taut ropes.
But how is it done with straight lines, though? Because wouldn't it have to curve around the planet?
No, that's the point. You've seen those patterns that they make with strings and so on, where you can produce a curve with many straight lines. That's what we're doing. That's the same thing we're proposing. We're saying that all this is done with taut ropes. It's just that what you have is that curvature because all the ropes are connected to each other. So you have this light coming through there. The image comes through relaying of the signals.
Okay, but I mean, you have a mess of lines going in all directions. But there is within that kind of chaos or order or whatever, there is this like you could select these lines that are at such angles that curve around the planet. But why?
Well, remember, you have a star, right? And that star is connected to all the ropes are connected to the atoms that form the corona. But see, that part of the corona now has that image because it has certain frequency that's coming from that star, and that's the frequency it relays to our camera. So that's why we can see the star, because it's a specific frequency that is different than the normal frequency that you find in the corona of our sun.
But our sun doesn't need to be involved, though, does it? Because we're on Earth, we're looking at the star, we have the eclipse, and then we have the light from the star. The sun is like, our sun's not that important in this
Well, I mean, you can do it with, all I'm saying, it's done all, whether you use a star or you use something as big as the sun, which is much closer, that's why it's just bigger. It doesn't matter. You can do it with almost any object, especially luminous objects like stars. What I'm saying is all done with straight lines. Why? Because the ropes are always taut. They're always pulled taut. And all you're doing is sending frequency. In other words, shorter links and higher number of links increases, so you have higher frequency, and that's what we're receiving through the ropes. The ropes are already in place. All we're doing is receiving the signal through the ropes. Nothing is moving in the sense of no physical object is really traveling. All you have is a signal, a disturbance propagating along the rope.
Yeah. Okay. So
that's what we call a photon. Here's a photon. You want to see a photon? Let me show you a photon. Here's a photon, one link of the rope. There's your photon.
Yes. Well, yeah, I mean, that's fine. It's a quantization.
Okay. So let me put this in perspective. So you have every atom, everything is connected by every other atom by a rope, right? So yes, what makes it closer is the torsion. The torsion changes. It pulls rope to one side and then pulls away from the other one. The other one, the torsion is the other direction. So the torsion is doing the job of pulling the thing towards it or away from it.
No. Remember, there's no pull. As far as the rope model is concerned, for gravity at least, there's no pull. Okay, there is no pull. What we have is tension. Tension is not a force, as it is in the religion of mathematics. Tension means that nobody wins the tug of war. Push, someone wins the tug of war. Pull, someone wins the tug of war. Tension, no one wins the tug of war. Okay, so that means you can think of tension as a dumbbell. You know, at the gym, the dumbbell is there. It's under tension. That's the sense of tension. There's no motion of neither of the weights in the direction of the other. Okay, so
it's like always surface tension.
I'm sorry.
Is it like a surface tension, Bill?
Well, surface tension is something, see, people think of tension as something that varies. They say, oh, the tension is, and they measure the tension. In science, we don't measure tension. In science, we define tension as no one wins the tug of war. There is no force. And so what we have is a static scenario. Now, what happens is the atom slides along the rope, like I explained earlier, like a bead on an abacus. But meanwhile, it's always under tension. Okay, it's always under tension, and the tension is given by little c. That is the tension of the rope. 300,000 kilometers per second gives you the tension on the rope in the sense that it's a constant. It's a constant tension. And all you're changing really is the frequency for the wavelength, the number of links versus the link length. That's all that's changing. But the ropes are in place. And so, you know, they're always taut, not straight, but taut. They're pulled tight. And so when you're talking about, for example, gravitational lensing, all you have is links there, signals going along the ropes to the corona of the sun. That's maybe the best example. And then to your eye. And you can do that with almost any star out there and say there's gravitational lensing. Why? Because all the ropes are conveying signals from that faraway star to your eyes or through whatever objects in between.
Okay. So suppose we consider comet. Comet is moving away from one side of a galaxy or something to another side
here's
of the
a comet
galaxy.
going around the sun. It's tied to the sun. That's why it's coming around the sun, because it's tied to the sun.
But it can move away from it. It can move to another galaxy sometimes.
I'm sorry?
Some of them can move to another galaxy.
Yeah.
What?
So how does it do
comet?
that?
You're saying the comet?
Comet
it
or
doesn't.
any other
It doesn't. But look, Rajan, listen to this, because this will give you a better image. Let's not talk about comets. It's too little, and you're wondering if it goes to another galaxy. Let's go with something simple. Why, when a galaxy rotates, why don't the stars go flying out of the galaxy? What keeps them there? What prevents the stars from flying out? And I'm saying they're all connected to each other. You have a rotating platform. That's what a galaxy is. That's why it's flat. because you have not only the stars, most of them along a given plane, but then you have on top of that the galactic magnetic field, which is extremely enormous, made out of threads. The threads that are being swung around the galaxy, it keeps the integrity of the galaxy, on top of the fact that all stars, every atom of the star is connected to all other stars. So you have a carousel. That's what you have.
Well, that's interesting because Rajan, you're kind of talking about something like that.
The magnetic thing. Yeah. So you are coming to, that's my main point. The magnetic thing is the main point. But what I'm talking is sometimes they can come closer, sometimes they can go away. How does that happen? Objects, the astro objects.
Yeah, but remember for example, Halley's Comet. Why does it come back every 75 years? Well, because it's being swung around the Earth, the sun, the solar system, and it's just got an elongated, elliptical orbit. It comes closer to the sun and goes out. Why? Because it's swinging it around. That's what's happening. So not all objects go in a circular way. And one of the reasons for that is that the sun itself is moving around the galaxy. So hopefully everything is elliptical and not circular. If the sun is moving, like imagine this, you're a cowboy, right? And you're on a horse and you got your lasso, right?
Yeah.
Well, if your horse is moving, that lasso is not going to be a perfect circle. It's going to be elongated. It's going to be a certain oval, elliptical. And I think that's what's happening to little items like comets, because they're swung around, but they're little. And so they have these, what do you call them? Orbits. What's the word I'm looking for? Exotic. There's another word. But exotic orbits, that are elongated in one direction. The further you go out, you get Pluto. It's got this weird orbit also. You know why? Because it's farther away from the sun. So it's a little tiny ball that's being swung around. That's all it is.
Well, it's a bit like the Mercury perihelion shift we talked about. That's a weird one, isn't it, Bill?
It's not. Listen, Chris, listen. You take this ball, okay? You do this experiment at home. This is one experiment you can do. Put a long cord, and then grab your cord very close by and try to do it. And it goes like this. It goes in a different way. Now, if you have a longer ring, it's easier to a smoother curve. But if you get it very close by, right? If you get it very close by, you get this.
Okay. I think it could be something like that. Yeah, that's interesting. I like it. I like it as an idea. So Rajan, what do you think? I've got to get another drink here.
Okay.
You guys,
you want to take a break, or do you want to finish it off? You want to take a break, come back?
I don't mind. I don't mind.
10 minutes break.
I think the debate part is over. We could just chill.
Okay.
I do have to grab some stuff, so maybe I'll jump out of this talk and then come back. Is that all right?
No, we can take a 5 minutes, 5 to 10 minutes break.
5-minute break. 5-minute beer break.
Yes. Okay. Nice. Okay.
I need a refill.
Okay.
Yeah, you get thirsty work, Cool.
Sí. Y están muy ricas esas paltas. Oh, sí, a mí me encanta. No he comido ni una todavía. No has comido ni una. No, de puras promesas. Pero mira bastante. Pero no hay ni una, mira vos. Acá dos o tres. Sí. Toma. Antes de tirarlas también el dulce. Pero saca las que quieras. Ahí está. Si la lleva a la mecánica, ¿qué es mi plato? Sí, cuchillo, sí, también. La nena británica hoy quedó tan feliz, así que va con nosotros mañana. Ah, pero va a venir. Gracias, Marisa, gracias. Escucha, este es el cuchillo que nosotros. Sí. ¿Qué más quieres? ¿Qué más necesitas? Pero te voy a vaciar esa. ¿Qué más? ¿Qué más? Ah, cuchara. Ahí.
So, I don't know whether Christopher is back, but so I mean, Christopher comes back, but what I have is that so these objects are not static; they're in space. They're dynamic because of the torsion in the. They're dynamically moving around, right?
Yeah, I mean, you're talking about the objects or what?
Yeah, the objects, the astro objects.
The atoms are not static. The atoms move around, but what I'm saying is that the ropes are under tension no matter which way they go, and they slide along ropes like beads on an abacus. In fact, I just uploaded there. Do you see that, Rajan? Do you see the
not yet?
link?
No, not yet. Not yet.
If you look at the studio chat, there's the second link. The second link.
Okay.
If you touch that, you will see the construction of the rope of the atoms and the rope.
Okay. Yeah, I can probably upload. Let me see whether I can upload to. Yeah. I may be able to upload. Let me check. I used to be able to do that. Check.
I'm able to see it. If you see that second link, right click on it. You should be able to see the how the rope model builds the atom and the rope.
Yeah, I can see that, but I'm trying to see whether I can upload it. So everybody
can't
can
you
see
do
it.
a right click on that and open up in another?
Yeah. Yeah, actually I'm doing that.
Because it'll show you how it's built. A picture's worth a million words.
Yeah. Oh, I can actually upload through here. So let me check. So I think
I think you can right click on it and watch it on a separate page, on a separate link. Where are you located at, Rajan?
In Arizona, United States.
You're in Arizona. That's where we have our house. We're in
really?
Arizona.
Where?
Yeah, in Mesa.
Huh?
We have our house in Mesa.
Mesa, I'm not too far. I'm in Tempe. You know Tempe, right?
Oh, you're in Tempe. Yeah.
Were you here? I mean, do you come here often?
No, I can't go there at all.
Mesa, you have somebody living here in Mesa?
Yeah. I have my house over there.
What do you do
It's
with that
amazing.
house now? What do you do
I'm
with that
sorry?
house? Are you renting? Are you renting the house?
No,
Are you?
my wife has the house over there. She travels and we meet elsewhere. She's coming tomorrow morning. She's coming here to Chile.
Oh, is she
Uh,
American or
do,
is she
do you know my
German?
story, or you apparently don't know my story?
I don't know your full story. No, I know
What
some of it.
you should do is send me an email or whatever, get in contact with me, and I'll send you a link to the movie they made of my life,
Oh,
and then you'll understand.
oh. So you were in the United States. Were you in the
Yeah.
United?
But they kicked me out.
Oh, I heard that.
They,
And then you are in Chile. You are in Chile now.
yeah, right now. No, well, I live in Germany,
Oh, so you come
but
to,
I
from
mean,
Germany to Chile? You come
no,
from
I'm just
Germany?
vacationing here.
Oh, so you go back to Germany.
Yeah. I got to go back on the second. I'm going back to Germany.
Oh, so your permanent home is in Germany.
Right.
Oh, I
But
see.
I have my house in Phoenix, in
Oh,
Mesa.
your wife is also German? Is she German?
No, my wife is from Colombia.
Oh, okay. So you can go
And
to Colombia also, right? You go to
yeah, I
Colombia
can go to
also.
I can go to Colombia.
Oh, okay.
In fact, I lived in Colombia for 2.5 years
It's
one
interesting.
time. But no,
Mm.
you got to watch the movie.
Okay.
If you give me an email, I can send you the link to the movie.
Let me put it in the chat. I'll
Okay, yeah, put it in the chat, and I'll send you a link to the movie.
Okay.
And that goes for Chris as well, you know.
Okay. Let me put my email.
Yeah, you can also look me up on Wikipedia. Just Bill Gady,
Oh.
and you'll find the story of my life there, more or
Oh,
less.
really? Oh, okay.
Yeah.
So can you see it now
What the what?
in the chat? My email address.
Oh yeah. Okay, so let me send it to you. Let me
Okay.
send it to you here, Rajan.
Okay.
Send you the link to the movie so you can watch it tonight.
Okay.
Yeah, in fact, my wife left a few hours ago from Mesa.
Oh, really? Oh.
Yeah. She went to Dallas and from Dallas to Chile.
Oh, so she'll be tomorrow. She'll be there. Okay.
Yeah, she'll be here tomorrow morning.
Okay. That's good. So you will when you are going back 2nd of January to Germany. Is
Yeah,
that true?
correct. Correct.
Oh, okay.
Correct.
Then you come back much later, right?
No, not to
Summer.
Chile. No, we're just spending here with some friends well, it's a little town outside of Santiago.
Uh, so you will be in Germany most of the time after that.
Yeah, correct. Yeah, absolutely.
What part of Germany are you in?
I'm in Frankfurt.
Frankfurt. Oh, sometimes I
Yeah.
go via that route. I
I'm
go to
sorry.
India. Go to India and all via
Uh-huh.
Frankfurt sometime. Last time I went to the conference, I went via Frankfurt and
Oh, I
then
see.
Budapest to
Yeah, because
come.
a lot of flights that go through Frankfurt.
Yeah. If it is connected to, for example, the German airline, which is Lufthansa, right?
Yeah,
Lufthansa,
Lufthansa. Yeah, exactly. Yeah.
they go via Frankfurt.
Yep. Yeah. The Lufthansa connects you just about with everywhere.
Yeah. So that's interesting. Yeah.
Okay, here I'm sending you the movie. It's called El Crazy Che. That's in Spanish means the crazy Che. Like you heard of Che Guevara?
Ah,
Well, it's
yeah.
kind of like that. In Spanish, we say in Argentina we use the word Che. We always say
Aha.
Che to like hey, hey
Oh,
buddy,
okay. Yeah.
So
Yeah.
that's what Che means. It has no meaning. It's just to call someone's
Uh,
attention. Okay, here I'm
uh,
sending it to you. Here goes. You should be receiving it there in your email.
okay. Let me check. Uh, Not yet. Oh, yeah. There you go.
Okay. Well, all you
Uh,
got to do is touch the link and you'll watch the movie tonight.
Okay.
Then you'll know a little bit more about me.
Okay. 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 That sounds good. Yeah.
Yeah. So it was 2015 they made the movie.
Okay. Bill Gates. Okay. So yeah.
Chris.
Yes.
Hi.
You're aware of my story, of my life story, my bio?
Yes, I am. Yeah.
Because Rajan was not familiar with it. If you want, I can send you a link to the movie they made of my life.
Oh, great. Is this Crazy Che or something like that?
Right. Crazy Che. Did you see it?
I tried to look it up on Netflix, but it's no longer there. So, yeah.
No, it's on Amazon.Prime, but let me send it to you. I've got it here. I just sent it to Rajan. You want me to send it to you to your email?
Yeah.
Let me send you the link. Give me 1 second here. Let me send it to your link, okay? So that you can watch the movie. It's a very interesting story, by the way.
Yeah.
Okay, let's see here. I'll just answer your last letter, okay? Reply to Chris.
Then I have my drink. I can.
What are you drinking?
I'm just linking different cocktail juice.
Oh, nice. Oh, very good.
Yeah, cocktail. Yeah.
Cocktails.
So again, all of us, Happy New Year.
Happy New Year, guys.
Yeah,
Happy
same
New
to
Year,
you.
Bill. Okay.
There you go, Chris. See if you received it.
Okay, I'll check it out now.
I think I sent it. Let's see. You should see a link there.
Well, this is it. I don't know if you ever watched James Bond or anything like that, Bill.
Well, that's more or less that's the story of my life, James Bond.
Oh, really? Really?
Yeah.
Wow.
Spying.
So which country you are? Which all countries were you in? You are in US, Colombia.
I was in the US. Yeah, sure, for many years.
Colombia, then Chile, Germany. Any other country?
Yeah, I lived in Colombia. I lived in Germany, Argentina, the U.S. Primarily those 4 countries. But I've been to many countries. Cuba sent me around to many countries, Mr. Fidel Castro.
Oh, really? Cuba?
Yeah. Oh. And then I worked with the CIA and the FBI.
Oh, really? You are an agent? Were you a CIA
yeah,
agent?
Well, I was an asset or an asshole. I don't know which one.
Wow.
Yeah, watch the movie. You'll like it. It's an interesting story.
You can also read on Bill's website. He has.
Yeah.
I think it's more from your perspective, is it, Bill? Like, you have a different take on what happened,
right? Because when they make these stories, like for movies, or when they write books or write articles, they miss a lot of points that are important, and people don't get the real story of what happened. And so I created a website. You can go in there, and you can. It's in. Maybe I should send you a link. I'll send you both a link later on.
Sorry, Bill. It's all in the description, along with your Patreon and all of that.
Oh, okay.
Yeah.
Okay, yeah.
You have your own website called "You Stupid Relativist" or something like that, or is this
who is a relative?
Your website is called. Well, it's the rope. I've
got 2 websites. One is called YouStupidRelativist.com, and the other one is called The Rope Hypothesis.
Yeah, okay, yeah, but the one of them just links to the other, as far as I'm aware. Like, Rope Hypothesis just links straight to You Stupid Relativist. I think.
Yeah, there's a link there, but the You Stupid Relativist is I haven't touched that in a long time. That gives you an idea in general of the theory, and then the Rope Hypothesis does more or less the same thing. Yeah, I've got 2 websites.
Oh, okay. Sorry, when I said link, I meant redirect. Like if you click on one link. Yeah.
I think I do. I got to check my Rope Hypothesis, which is the newer website, to see if it's got a link to the to YouStupidRelativist.com.
Okay, yeah, it's fair enough. So I was reading on that, and it does seem more complicated because you've got all of these. Well, not that I haven't actually watched El Crazy Che, but.
You should watch it. You should watch it. You'll like it.
I was
It
looking
won a
for
couple prizes, international prizes. For the
Really?
movie.
fantastic. Yeah, I don't know if I looked for it on YouTube, but I was checking Netflix and I was looking for it on tour sites, and I don't know. I maybe I just never typed it into YouTube.
Did you get the link, Chris? Did you get the link?
Yeah, it goes to your other channel on YouTube.
Right. It goes to Bill Gady. Yeah. So
Yeah.
watch it tonight, and you'll see the story of my life a little bit there.
Oh, fantastic! Yeah, and then of course, so the complexity that I noted, where things start getting confusing, is with all of these defectors from Cuba, and then they get captured, or no, they decide to come back to America under some deal or something, and Obama's involved, and yeah, that was a little bit strange. But it sounds like you went to Cuba, and then or Castro was inviting you over at one point.
Yeah, Fidel Castro invited us. He wanted to meet my wife and me.
Yes. And so, yeah, your wife was with you. And then you went to stay in some hotel. And, or so you became disillusioned with Cuba because it was like people were living in poverty over there. It was pretty terrible. And then.
Well, no, I had already made up my mind before then. You know, the Eastern world, the Soviet world.
Yes.
What is called the Pact of Varsovia, which is the military counterpart to the NATO. Okay, so they had the Varsovia Pact, and essentially, I was helping them out. I was helping the East, the communists. I was a communist for many years in Argentina, and when I went to the States, I started helping them out. That's how I got in touch with Fidel Castro and his regime. But then. They turned me around. They tried to use me against the United States. I turned myself into the CIA, and the CIA started using me against Fidel Castro, and I became a pawn in their game.
Yes,
very interesting story.
Were you in Russia also, Bill? Were you in Russia also? Were you in Russia?
Where?
Russia.
Russia. What is that?
Russia. Soviet Union.
Oh, no, I haven't been to the Soviet Union, but all the material that I gave them there, they're very happy.
For sure, yeah. So this first Soviet thing, that's gone then, is it? Only NATO exists?
Yeah, no, Soviet is gone, but, you know, you had the KGB, which is what I worked with essentially indirectly through Cuba. And now they have a different name, like, you know, I can't remember the name right now.
KGB,
but they've got different acronym.
Yes, no, that's right. No, I know, like the Soviet Union obviously collapsed back in the late 80s, early 90s, I think it was. But I was just talking about this pact because, you know, like, you know, the NATO agreement. If a country falls within NATO or something, NATO still survives. So I'm just wondering, why did it happen that because the Soviet Union collapses, their kind of NATO pact equivalent, this first Soviet thing, also disintegrated? Is that just because they lost the Cold War or something?
Yeah, they had a big problem over there in the Soviet Union where, you know, you have Gorbachev, Mikhail Gorbachev. He came to power, right? And he was trying to loosen up the country with perestroika, you know, and this loosening of the tightening that they had in the communist world that came all the way from, you know, Stalin, Nikita Khrushchev, and Brezhnev, all these people. And so they held a tight rein over the country. And what Gorbachev did was open up the country, and a lot of the you could say the ultra right of the Communist Party, primarily the person who I was dealing with indirectly with the Cuban, which was Vladimir Kryuchkov. And Kryuchkov was the head of the KGB. And he was the prime man in what is called the Group of Eight, or the Gang of Eight, that were trying to overthrow Gorbachev. They almost overthrew him, but that's when Yeltsin stepped in and did a counter revolution and put those guys in prison. And they were in prison for a very short while. Then they finally let them go. And
they're the oligarchs.
The Soviet Union became Russia.
So they're not the oligarchs. They were a different bunch, were they?
Well, what it is, they wanted to maintain certain privileges, especially, and they wanted to run the country in a certain way where it was centralized, and all the little countries, the provinces, whatever you want to call them, the SSRs, they all wanted independence. They wanted to be governed independently, and that's what happened. You know, at work at AMD, we used to call it the UFFSR because it was the Union of Fewer Socialist Republics.
Wow.
Because they were breaking apart in 1989 all the way to 1991. It all broke apart, finally. But you know, that's history now.
Absolutely. Well, yeah. What do you think about the world's situation at the moment? The geopolitics.
Well, you know my theory. I'm writing a book right now. It has to do with homosexuality primarily, but it has to do with the end of the world. I'm saying we're the last humans on Earth.
Oh yeah.
That's I'm explaining why we're going to be the last humans on Earth.
Didn't you have a theory about homosexuality in ancient Greece or something? Or
yeah, obviously. I mean, I've got a problem with. I'm not into rights. I don't care about rights. I don't care about laws. I don't care if they have freedom or not. That's a subject I don't get into. That's politics. I don't get into politics. I'm more concerned about something else. The fact that the gay lobby, as I call it, what they're doing is modifying history and saying that all Greeks were gay, all Romans were gay, all Jews were gay in the past, right? No way. That's bullshit. That's a propaganda. And that's what the book is about. But it has to do also with extinction.
Right, but so is homosexuality part of extinction? I mean, it's
I'm saying that the last group ends up being homosexual in great measure, just in general terms, because we lose our genetic diversity. And so essentially anyone who you marry today is, from a genetic point of view, is either your sister or your brother genetically, right? So it doesn't matter if you marry an African or a Chinese or a South American. We all have, there's no genetic diversity in all the human race. There was a study about 10 years ago. They went to the chimpanzees that are in the region around where Nigeria is. There's a river there, and there's many troops. And they did it with a couple troops, and they found out that a troop of 100 chimpanzees has more genetic diversity than 8 billion people in the human race. How do you explain that? In other words, if they get married there's such genetic diversity, it doesn't affect them. But if we marry each other, and we've been doing that for the last 200, 300,000 years, all the effects are, you know what happens when you marry your sister and your kids marry between them and they marry between them, 2-3 generations later, you start having 6 fingers. And one of those genetic impacts is homosexuality. That's my theory in a nutshell.
Yeah, that makes sense. I mean,
I'm saying it's a genetic problem and we cannot avoid it. We're going to get more homosexuals and all kinds of people with mental problems in general coming up in the next few years.
Yeah, for sure.
I had a theory. I checked because I used to think from about finally I came to because I had something called matrix protocol. I came to the idea that all of us were Arabs, somewhere in Arabia, but then moved to different places because of the continental thing and then reborn again. So we lost the fact that we are all Arabs, and now different places because there are some traits. If you look into that, the traits, if you activate certain type of genetics, you can see that we have the same type of thought processes with a man and woman. Like you can actually think about Fatima, all the Mary, everything happened in the Middle East, right? And then you can tap into that by certain echo or certain signals, and you can see that person that becomes that. Although you will think that no, it cannot be that. You can prove that even Eskimo, will react to that Arab
well, like Mary was Jewish, not Arab, but really, like if we look at Arabs, I mean, what race? I don't think Arabs are necessarily like a full race.
I call it Arab.
So wait a second, Raja. Like the Caucasian race or the Aryan race kind of is linked from the Caucasus Mountains, which goes from like Ireland all the way down through
Uh-huh.
Czechoslovakia, or well, the Czech Republic and Hungary, and down that direction. And then that was the whole point of like Aryan, you know, supposed to have this link to like Iran, that they consider themselves Aryan, and then the Irish, you know, so you've got like it's Era, the country Era. We are Aryans as well. So I think that's
look at something, Chris. Listen to this. You take two dogs. You can take a German Shepherd, right? And you can take a Chihuahua. They're both dogs. Even though they look very differently morphologically, yes, they can have sex and viable children.
That's true,
okay?
Yeah.
Why? Because they're from the same race and their genes are not that different, even though they look so different as animals, right? Physically. Okay, so what's the story? The story is you have Chinese today, you have Japanese, you have black people in Africa primarily, right? And you have your white people in Europe and South America and so on, brown people, etc., right? Yeah. And you say, well, these are different races, but we're not. Let me tell you why. Yeah. Let me tell you why we're not really different races. Our great-grandfathers, let's take it one more step. Great-great-great-great-great-grandfathers, right? Take it several generations back. They were attacked by diseases. They got smallpox, they got whatever they got, yellow fever, anything that hit them, right? And what happened? Over time, we either overcame those diseases or developed vaccines, or we simply introduced better, living conditions, like better water. We didn't poop in the lakes and so on. So they cleaned up, they realized that you got to clean up the environment on the one hand, and on the other, you had to eat better, and again, they had vaccines, and there was also the issue that we went over, our great-grandfathers, the guy who survived the disease, he was immune after that. He passed that on to his kids and so on down the line. So what happens? It doesn't matter if you're born in Japan, if you're born in China, if you're born in Africa, if you're born in South America. Our great-grandfathers of all people living today passed through the same sifting mechanism of diseases. So it didn't matter what part of the planet you were in. You might think you're a different race. Hey, I'm Chinese. I got my slanted eyes. The other guy's white. The other guy's black. It doesn't matter. Our great-grandfathers, they passed through these same sifting mechanisms, which is the diseases. We don't have we don't die of childhood diseases. You don't die of rubiola. You don't die of chicken pox anymore. Those diseases don't kill us anymore. Why? It used to kill half the population 200 years ago. No, it doesn't happen anymore because our grandfathers passed through that sifting mechanism. He who died stayed behind, and most of the people that came forth were the ones who reproduced and became our great grandfathers. So you're immune today. You're not going to get a disease like scarlet fever or anymore like that, because it's no longer, childhood diseases don't kill us anymore. What kills us now is diseases of old age, arthritis, cancer, diabetes. That's what kills you. But we don't die of contagious diseases anymore. Once in a while we get a new one, maybe out there, but we don't die of the childhood diseases anymore. Everybody lives. So we're all the same genetically. We're all predisposed already to combat any disease that we used to have. They don't kill us anymore.
But what about, you're talking about species, right? Different species aren't able to interbreed and have viable offspring.
Right. You can't have children with a chimp or with a gorilla. Yeah. They're too far away in our dynastic lineage.
Yeah, but with like a horse and a mule or something, if it does have, or a horse and a donkey.
Mules are sterile. Why? Because it's it's the mixture between a donkey and a horse.
Yes, exactly. But so then, like with you could have like a species and then subspecies within that, different categories, and then they could interbreed. But so I think like the term for like subspecies in the human species, therefore, would be races. So it's just a different word. But I think like they do say that, you talk about like genetic diversity and not wanting to marry your sister or whatever. I think that's valid. But, there's an issue about maybe if you marry too far from your genetic center, let's say. So, for instance, if you were to marry a black woman, she has a much higher chance of having sickle cell anemia than your child with another European person, for example. So
maybe, you know, I mean, what we would have to do a genetic study of these two people, you know, and find out. But all I'm saying is we're not that different from blacks or Chinese or, you know, yellow people, brown people. We're all the same.
Yeah, but
genetically, we're not that different anymore.
I think, yeah, I don't know, but I think there's been like a good deal of separation between the different races.
We're not, Chris. Believe me. Look at the information. They do a DNA, you know, genetic analysis of chromosomes and so on around the planet. We're all the same.
Oh, okay.
You might look different than me or down there, but we're all the same. Genetically, we're not that different. Not anymore.
Yeah. Okay. So there's that argument you're making about the troop of chimpanzees in the jungle. They have much more genetic diversity. I think that's true of all animals in general. They're just way more diverse. But I mean, the human species is an odd thing. Like we're totally different to all the other animals on the planet.
And also, they are analyzed human genes. It's 90 to 99% chimpanzee, mostly, or something.
I don't know
like
if that's true. I mean, Bill, you've got this theory that we don't even have Neanderthal DNA in our, because we're not mixed with Neanderthals. It's just the fact that there are key bases that are the same as with Neanderthals, but that doesn't mean
we only have like 2% to 3% commonality with Neanderthal, and you can get that from 500,000, 6,000 years when our branches separated. In fact, even before that, look at something, and you can tell here that we could have never had sex with the Neanderthals. There was a Homo erectus. Homo erectus was already in England 800,000 to a million years ago. They have the footprints. They have animal bones that some animal hunted. It had to be our Homo ancestor. And the issue is that guy went to Arctic weather. Did he have clothes? Did he wear, you know, to live there? No, of course not. He was a hairy monkey. That's what he was. And he gave birth to Heidelberg, man of Heidelberg, who gave birth to man of Neanderthal. So if ever we encountered a Neanderthal, we would have been so different. We would have been dressed, and he would have been a monkey, you know, just a gorilla. And I don't think they would have had sex between them. It's just impossible.
But I think Homo sapiens were formed from Homo erectus, right? Is there a connection?
They're what? They were
we are Homo sapiens, right? Yeah. And then there is a connection between Homo sapien and Homo erectus.
Yeah, I mean, if you go 800,000, 1 million years ago, you're really talking about a million years ago. If you go to Southern Africa, you had a Homo erectus there that gave birth to another human ancestor that we had. I can't remember. Man of what was it? The Rhodesian man. That's what they call it. Rhodesian man was at the same level of evolution as man of Heidelberg. They were more or less the same level. And as far as they can tell for now, according to the very little information, you know, the very few bones they found, they say we descend from man of Rhodesian man. Maybe later they make a modification to that, but I think we came out of Africa. When we moved into Europe, we could not move in there because the Neanderthals would kill all of us. They were in their hometown, and we were invading their territory. So I don't think we would have gone in there just being invited and having sex with them. I mean, the worst enemy of a Neanderthal was another Neanderthal, and the worst enemy of a human was another human. You had your clan, that was your country, and the other clan, they had a different flag. You know, they had different interests. They had different territorial, interests. They hunted in their ground. You hunted in your ground. If you went into their ground, they would have killed you. You know, it's like a Russian meeting an American. They would kill each other.
Right,
I mean,
but then
it was a different country. So you can imagine all humans suddenly, you know, slowly moving or migrating into Europe. The only reason they made it is because the Neanderthals were dying or died. Then you can move into their territory. So I don't think we ever met a Neanderthal. If we did, he was a dead Neanderthal.
I don't know, though. But if we look at Africa, let's say, they recently found that there's a lot of what they've termed ghost hominid DNA in the African population. And they attribute it to intermixing with another earlier hominid that was about, and this is like recent, this is only in the last 20,000 to 50,000 years or something like that. So
yeah, but you know one thing, Chris. I looked at a lot of these papers. I read a lot of these papers, and one of the things you find from some of these researchers, the anthropologists and the paleontologists who look at these bones, they say that the Neanderthals mixed with some kind of human around in the region of Israel and Iraq. In that region, you find bones, and they say, "Oh, look, here's a Neanderthal, and they had kids with humans." But if you look at those bones, if you look at the facial, morphology and so on, they're not your traditional or Western, the classical Neanderthal that you find in Spain and France and Germany. These guys are different. So, a lot of these researchers claim that these are not Neanderthals. But see, those people who are bent on intermixing, what they call admixture, they're saying, "Oh yeah, we mated in the Levant, in Iraq and Israel." That's bullshit. I mean,
why would it have to be there? Why couldn't it be in?
No, and I'll tell you that it couldn't have been there because the Neanderthals, everybody moved into Europe because that's where the hunting ground was. Why would they move out of their hunting grounds? Like you're moving out of a castle to go into a shack. Why would you do that? Here you are in the land of plenty. You're in heaven, and you want to go to hell to a hotter climate in Israel for what? Why would a Neanderthal go down there? If anything,
the way there's different people, like if I was to look at a European and then I look at an African, right? We're saying, right, they're all people, but they do look different, and there's a lot of differences there, culturally and in terms of their interests.
Well, how about if you saw a gorilla? Would you
wait a second. So you could say the same thing about a Neanderthal in Europe and one in the Levant. They might just be like kind of different, but they're still Neanderthals. Is that possible?
Yeah, but remember, Neanderthal is a gorilla. He doesn't have any clothes on. He's from cold weather. He's from Arctic weather.
Well, then he'd be happy in the Levant, wouldn't he? Because he's naked already, so he's like sunny down there.
But I mean, he's not. First of all, he's not going to put any clothes on. But the question: why would he go into? Why would the polar bear go to the equator? That's the question.
Right, but okay. So you're saying that this thing is an animal, like it's not like a human. But didn't they find evidence of Neanderthal art? And wouldn't that suggest that they were more than an animal?
Look, it's debatable. First of all, maybe they did some art. Maybe they did have a big brain case. In fact, their brain was bigger than ours. That doesn't make them really more sophisticated, intelligent-wise, but they did have a big brain, so they have big capacity. But what was the brain used for? They used it for hunting. They created these lances, these spears, very rudimentary spears with which they stabbed the classical Neanderthal. They would stab maybe a woolly mammoth or a woolly rhinoceros or whatever. And they would, it was a group activity. They would stab the thing while one guy acted as a circus clown. He distracted the animal. The other guys came from the side and stabbed it. Okay. So now the clan gets to eat. So that's what they used their intelligence for. They didn't do any sophisticated thinking,
But that's what you're talking about there. You've got tool making. We're saying art is an option. We've got sophisticated planning, possibly communication. So they probably had language. Really, I'm not seeing a whole difference between us and Neanderthals. I mean,
well, I'll give you a difference. Here's the difference. Tell me how a Neanderthal had sex with a human, whether it's male with female human or male human with female Neanderthal. Well, how would they do that? Tell me how they would do it in the wild.
Right. You've heard the theory. This theory of, I've forgotten the guy's name, but he came up with this idea that Neanderthals were this monster with like huge eyes. And
I know who you're talking about. I know. Yeah.
Yeah, I've forgotten the details, but it's like this monster creature, and it
Yeah, you can look it up. He's got his website. It's called Them and Us. Them and
right.
Us.
Okay, that's good. The viewers will, in the future will be watching this. So this is the point. So we did have So the point is, so I think his theory is that they came in, they were like raiding, and they would rape, so there'd be like interbreeding that way. It's a bit of a weird one.
You can't rape. You can't rape in the wild. You cannot rape. It's not so easy to rape in the wild. Imagine, listen to this. You're part of a clan. You're a woman or you're a man part of a clan, right? There's maybe 15 people, 20 people in that clan. They move together. They hunt together. They live together. The woman, especially the woman, but any member of that clan, whether it's a child, a woman, or a man, you cannot stray too far all by yourself from the clan for various reasons. You may encounter a lion. Remember, it's in the wild. You encounter an animal. You should be able to be within shouting distance with your clan. You should be able to say, "Help! 911, come and help me!" So you need to be relatively within shouting distance. You're not going to stray all the way to the middle of the field and have a Neanderthal rape you, and then come back to the clan and say, "Hey, there was this monkey that raped me."
We're talking about like raids of one group comes in, raids the other, grabs the women, let's say, brings them to their location, and then incorporates them into their society briefly, and then their offspring. So there's that possibility, and then you would have like a mix of human and Neanderthal.
The gorillas,
and those people would form their own societies and then interact with the humans, and then the humans would be like, "Hey, are they Neanderthals or are they humans?" And then they wouldn't really know, and then they'd be just like, sure, we'll just hang out with them. They seem okay anyway, and they're kicking the ass of the Neanderthals for us. But I have a different theory that's kind of connected though to this us and them guys group, because if you think about it, he had them with these like huge eyes because he looked at the skull, didn't he, and then decided, hey, I'm going to reconstruct their facial features based on their skull, and then he did that, and he came up with the kind of monster creature that we see.
But everybody has a different. I think everybody came up with something different.
Yeah, but I think his approach is good, though. I think his approach was good, Bill, because I'm looking at that skull, and then you look at the humans, and then you look at the reconstruction.
But that's my point. My point is what you just mentioned about, one group attacking another. Chimps do that all the time. They attack another group of chimps. They kill the males and they take the female, especially the young females, as hostages, and they become their wives and whatever. But it's chimp with chimp. Neanderthals did it with Neanderthals. A human might have done it with with humans. The question is whether humans would go after monkeys known as Neanderthals and do that to them, or vice versa. I don't think so.
Well, maybe
gorillas don't go and attack chimps, and chimps don't attack gorillas.
Well, maybe vice versa, though. But I'm thinking though. Here's my theory, but based on the guy's facial reconstruction of the Neanderthal, which I thought was actually kind of convincing. I'm convinced by that. So if you look at them, they have these like really big eyes, and you're thinking, well, why do they need these big eyes? And then I was thinking, so my theory is that Neanderthals were nocturnal animal, so they were like fitting into a niche of like human hominid, but totally nocturnal. And so when the white, when the Homo sapiens came in to become Europeans, I guess, they would have been operating during the day. And then at night, these guys would come out, there'd be raids, and they'd be like, oh crap, we got a problem here. But because the people were operating during the day, they had a lot more advantages. They started to, fire, and they were able to create better weapons in the light. And then they would also do raids at night. And then that's how they were able to wipe out all the Neanderthals, but not before interbreeding occurred. That's a possibility.
Yeah, but the question whether they would interbreed with a different species, that's what you got to find out whether they had any breeding capability at all.
But what about these African hominid things in South Africa? If they are interbreeding like around 20,000 years ago. This idea that like we always say like, oh, Africans are like the old thing, which is kind of a racist idea when you think about it, because it was based on the chain of being, was it? Where you had like angels at the top, well, God at the top, then angels, then man, and then animals. And they were when they first went to Africa, they expected the place to be just full of riches and palaces. And they were like, oh, this is going to be amazing. And the stuff we're going to learn from these people is going to be insane. And then because they thought that because of reading the Bible with the Queen of Sheba and all that. So they were expecting palatial stuff. When they got there, they found guys living in little makeshift huts and just no agriculture, hadn't invented the wheel, not even writing. They hadn't even invented writing. So they were like, okay, we're well disappointed here. And then they go into the forest and they met this, they were told, oh, there's a man who lives in the forest who's called the man of the forest. And he is, and their word for it was orangutan. So they went, oh, let's go meet this guy. So they go in and they're like, is that a man? And then they're like, if that's a man, then are the people living in the stick huts, are they also men, or are they both animals? And then they just said, right, it goes Europeans, Africans, orangutans, and Africans wear the missing link, you know? And, you know, if we're saying that they are like a recent addition to the human race in the sense that they're newly mixed with some hominid, then you could kind of think of them, well, so it's kind of a separate point. It's like, they're not our ancestors in a strict sense. They're more like the newest addition to the human race, I would say, from a genetic point of view, which is pretty cool because it means they've got a lot of overhead in terms of when they could develop way beyond us, you know, given enough time, I guess. But at the moment, I'm thinking that probably like the Chinese are interesting because they bought into the whole evolutionary theory, and you know they've got an incredible fossil record. But they haven't been able to find the missing link and loads of other things, where gradual evolution from simple life forms, they can't find that either. But in their opinion,
they don't have ancient, at least so far they haven't found any. They looked, but they don't have ancient hominids such as, you know, what they have in Africa. Africa, you not only have Homo erectus, but you had before that 2 million years ago Homo habilis. And there's no Homo habilis in China or in the East.
Well, that's an interesting point because, you know, I heard, so they have a theory that life or humanity began in China, which makes sense because they're Chinese and they want their region to be the origin of everything.
Nationalism, not science.
Yeah, so you can understand where they're coming, like why would they would have that viewpoint. But then there's another opinion that the people in the Aborigines in Australia are actually an indigenous people to that region. And they would say the same thing. They're like, yeah, we're the first people. We've been around for the longest. We've got the oldest stories, the whole thing about.
Yeah, but you know, a lot of that, if you don't find any bones, like, you know, the Aborigines, if you go there and you look back in time, you won't find, at some point, you go maybe up to Homo erectus. You can't go beyond that. I mean, the oldest hominids we have, if they're part of our lineage, because we don't have evidence of that either, all we have is theories, are the Homo habilis, you know, and they've been around 2 million to 3 million years ago. And you know.
Right. This is the thing I heard is that, like, let's say you had a Homo erectus and then they moved into whatever the Aborigines are. So that the Aborigines are like a type of Homo sapien or something. And then they moved out of Australia into Philippines, those areas.
But there's China. But we need to find the missing links. There's no missing links. I mean, that's a great story, but the question is, do we have any evidence of that? There is none.
How about the cavemen?
Just one point. So when they came in, they apparently, this is what I heard. I read this somewhere. They interbred with a hominid in that region. And then what happened after that is the Aborigines were kind of disgusted by what had occurred. So when they started meeting the other people, they were like, yeah, we don't like you. We think you're weird. Go away or whatever. So they remained sort of isolated. And then from there, like everything just sort of
Yeah, but you know what's wrong with that? That sounds like the Bible. The Bible says that Adam and Eve, they had a kid, and that kid grew up, killed his brother, and then he went to the land of Nod and found a woman. Hold it. Where did she come from? If they were the first people on Earth. And you're telling me more or less the same thing. The guy is over there, found an Aborigine. Where did he come from?
well, this is it. No, the Aborigine, because you're saying that there's not much of a fossil record. So you've got like, oh yeah, I see what you mean.
At least there's no evidence. That's all I'm saying. Yeah. I mean, we can concoct any story, but unless you find some bone there that says, okay, it's in such and such layer of the rock, it's 1 million years ago. Yeah, this could be, a missing link. But if you don't find any missing link, you go from Homo erectus to the fellow, the Aborigine. There's a big gap there. You got
that's valid. I will say something about the Bible though, because I've noticed that thing. But if you think about it, you had the Garden of Eden, which is it's like when God created man and woman. Yeah. They were in a perfect state, and then they ate the apple and then they fell. So it's like they went from one dimension of like no death and all this, and then they came to Earth, which is like a place of death and whatever. And so there was already people here. They just other people who live and die. So that's why.
But that's okay. But we miss all that part in the Bible because there's no connection between Adam and Eve and how the rest of the world came to be. All of a sudden they go into the land of Eden, that region there, which I guess was Mesopotamia, and they already found people. They found this population there.
Yeah, but there just seems to be like this idea of the fall. So I think of that as a fall from like a state of energy, if you like, or being, and then you arrive on a fallen Earth, which is like, and there just happens to be people here because, like, if you were to fall again into hell, there's still like billions of souls in hell. It's like, where do they all come from? If Adam and Eve were the first people, well, they've just been falling into hell, and that's the reason why the story of the Bible is so important, because you've got this like evil, jealous God for a while. And then Jesus kind of comes along and says, hang on, this is all craziness. And then says, I'm going to save you guys. Because if you follow this Bible thing, you're all going to go to hell, because there's no way that you can possibly follow these rules. They're so draconian. Like you can't even switch on a light switch on a Saturday. What's this about? Where you go to hell. You can't wear fabric made of 2 different fibers, or you go to hell. You can't eat a bacon sandwich. Can't eat a cheeseburger. I mean, it's ridiculous. So everyone's going to hell. So Jesus said, here, just believe in me and you'll be all right. And that's it. Yeah. And then he was killed, and then he went to hell, and he opened the gates and freed everyone. And then came back to life and said, yeah, I overcame death. I am the man. And then that's the story. And if you don't believe that, you're going to hell, Bill.
Yeah, no. I'll put the question to you, Chris. Okay, we're almost New Year's, right? Tomorrow. Are we living in heaven or in hell?
We're in between, right? And that's what.
Well, I don't know about you. Outside, it's heaven here. Heaven, absolutely. It's beautiful. But then you have the real world out there: politics, killing, murder. That's the hell part. Yeah. So in a way, we're sharing a little bit of both.
I agree, but that's the whole mix thing, isn't it? And like we're halfway between, and that's what makes us kind of important in terms of we have the ability to choose between right and wrong, and we have both options here on Earth. But then you also have the story Cain and Abel, and Cain gets marked, and then his seed proliferates on the earth, and that's sort of like, so there's 2 different groups of people. There's like the evil people, and then the good people, the people of God. And
it's the politicians and the rest of the world. Yeah, that's
right. So whatever it is, but there's definitely evil people among us, and I think all of us like have both sides, and we need to choose which side is the one we're going for, and then you'll be seated either on the right side or the left side, and you'll be judged at the end. And that all makes sense to me. But the point is, I think Jesus says something like, he can't just come down and separate the wheat from the chaff, because if he does that, it will harm the good people. So he has to. So you have to wait until a certain event. I guess like when have you read the Book of Revelations?
Yeah,
that's all going to happen.
I read the Bible twice.
Wow,
twice. I read from beginning to end. I love the book. I really, but I look at it from a historical point of view. You know how people thought in those days. But I like the book.
I believe that the events as described in Revelation are going to occur, and I think they're rapidly on the way. In fact, the interesting
we're the last humans on Earth. We're the last humans on Earth.
Yeah,
the last generation.
Yes, I think I'd agree with that. I think it's going to occur. I don't know when, maybe in the next 30 years or less. But so the point is, the point I'm trying to make is, if you look at this whole story about the mark of the beast, and then Christians say, oh, that is going to be some kind of technological thing, like a microchip in the wrist or something like that, and it will, you won't be able to buy or sell. That has connections with barcodes as well. But the point I'm trying to make there is that Christianity, despite it being 2,000 years old, is the most modern religion on earth, because it's talking about things like man will create an image of himself. And now people are interpreting that as, well, that could be AI, because it's a literal image of who we are consciously. Yeah, and they say that thing, that in the book, it says that the image will kill almost everyone on earth. Or no, it would kill everyone on earth if God didn't step in and stop it at some point.
Yeah, but Chris, I have a better, more down-to-earth theory. This is not an issue of prediction, not an issue of a prophecy and saying, oh, on the 1st of May of the year 2030, we're all going to die. It's not, or the last man is going to die. It's nothing like that. It's got to do with something else. It's got nothing to do with intervention by super human beings or whatever. It's got to do with something else. We have a global economy, okay? And that economy, in a nutshell, is going to collapse. We cannot continue it's called an inverted pyramid scheme, right? Yes. It's a Ponzi scheme, but in reverse, where, that's our human economy. We expect to sell more next year because there's got to be more population next year, right? And that's the perspective, that's the projection. So the car company says, okay, we're going to sell more cars next year. The people who build houses, we're going to build more houses because there's going to be more people next year, and so on down the line, right? Okay, what happens? It turns out that now the growth of the world population is asymptotic. It's approaching the asymptote, right? So we're flattening out our curve. We're having fewer and fewer kids. The population is becoming older, and we're having fewer kids, partly because we moved to the cities. In your cities, in an apartment, you cannot have 10 children. Okay, like in the country. In the country, our great-grandmothers, they had 10 children. Half of them died. Nobody cared. 5 of them survived. They kept going. Today, we don't even have one. And when we have one, we treat it like God, because, it's the only human you're going to have. You're not going to have 2 of them. Certainly, you're not going to have 10, all right? And so on. We stop having children. What happens? The population pyramid overturns. More older people, fewer younger people. And what you have is that population inversion. What happens? At that point, we stop having kids, or have fewer and fewer kids. Proportionally, we do not replace the population. But what happens economically? The companies don't sell, because now you have an inverted pyramid scheme. Now it's not that you're going to have more people in the future. You're going to have fewer people in the future. So now companies start closing their doors. Add to that, you have better technology, so you need fewer people. Maybe you bring the AI in there. That's even worse. So now you get rid of people from the jobs. Now what do these people do? Well, they starve to death, and so now the government has to maintain them from taxes collected from the few that still work. And you cannot continue. And who, by the way, whose real wages have dropped in the last 40, 50 years. So not only have real wages dropped, we have fewer jobs, and we have more people who are dependent on the government. everywhere in the world. This is happening worldwide. We can't even stop the process. You cannot continue that process forever. At some point, the global economy will collapse. And what I mean by that is money is no more. We will no longer believe in money. If I were to buy your house, and say, hey, Chris, I'll buy your house and I'll give you $1 million, but they're all Vietnamese money. Will you accept it?
Vietnamese money. And what's the exchange rate there?
By the way, it's called the dong. I'll give you $1 million dongs. Okay, will you accept it for your house? And then you say, that's not money. What do you mean it's not money? It's backed by the government of Vietnam. What are you talking about? But yeah, you don't accept dongs. You don't accept pesos, Argentine or Chilean pesos, because it's not money for you. You don't care about that. That's not money for you. You cannot go to the supermarket and do something with that money, right? And so imagine now the dollar, the euro, whatever, currency you're in, suddenly has that notion where you want to go to the store and you say, I want to buy a potato. And they say, well, what are you going to give me? I'm going to give you money. Here, what do you want? Bitcoin, gold, I'll give you $1,000. What do you have? That's not money. That's just a medium that we gave value to. It has no intrinsic value. And suddenly, if the global economy collapses, what do we mean by that? Money is no more. You don't accept money. So the producer doesn't produce food. The distributor doesn't distribute food, because what are you going to pay him with? The supermarket doesn't, stock up and sell stuff. You don't go to work, because what are they going to pay you with? Money? I mean, what the hell? And so money dies. When money dies, we're no more, because we die of starvation. We die like all other animals in the past died, from the collapse of the real economy, the natural economy, food. A mass extinction, that's why I had to define that term. Nobody defined it. Mass extinction, the disappearance of a food chain.
Yeah, because you talk about that in the past. Like, what was the reason for the K2 boundary, or whatever it's called, with the
KT,
yeah.
And very simple, very simple. If you look at, I've got a graph that you look at the graph and you understand it immediately. Carboniferous, what happened? What died? Well, what died were the plants that existed up to that point, which dealt with spores. They reproduced by spores. They were around for millions of years, and the animals that ate them were the herbivores that were amphibians that also, ate flies and other insects, dragonflies that were around in those days. So there was this whole world. That world collapsed. What continued were the mammal-like reptiles, the synapsids. They continued on to the Permian. What happened at the Permian? Well, you have the glossopterids, and they died, and that was almost all there was to eat in Gondwana land, which was the southern part of that world at the time. That was the only plant there was, and it was a seed fern. When glossopterids disappeared, guess what? The mammal-like reptiles disappeared. What happened in the Triassic? You had the dicroidiums. The dicroidium was another type of seed fern that covered the land. When they died, all the crocodile animals that lived at the time, they went away with them. What happened? What continued? The dinosaurs into the Jurassic. What happened to them? Well, you have the the cycad-likes, like Williamsonias and so on, that died. And guess who disappeared? The dinosaurs disappeared. And then you get to the end of the Cretaceous. What died? The dinosaurs. Why? Because the conifers died. Who took over? The angiosperms. That's what we eat, the mammals. So a mass extinction is a chronological extinction. It always, without exception, takes care of the old and allows the new to continue. The old food chain disappears. The new food chain continues. No comet, no climate change, nothing can do that effect. Only that's nature. That's Mother Nature. The plant disappears, you disappear.
Right,
and
but
that's chain collapse. We're going to die because food disappears, because we produce the food that we eat, and we produce it only for money. No money, no food. That's how simple it is.
Right, yeah. So that's your extinction mechanism idea. But So it kind of reminds me of, you know, the way the physicists talk about, I'll tell you how the universe began. You have to give me.
No, tell me how matter was created. How to get God? I'll even give you God with his magic wand. You know, just go in there and have God move his magic wand, right?
Yes, but that's
and I want to know the mechanism of how you turn nothing into something.
Well, that's the point. Give me one miracle, says the physicist, and I will show you how everything else comes from that. But they need the first miracle, which is the Big Bang.
But that's what I'm saying. You cannot create matter. So I'm saying that the matter that we have, all atoms that are out there in the universe, they were always there. There was never a first atom created in the universe.
Well,
you know the worst part of that? Let me tell you what the worst part of that. But if I tell you this, you won't be able to sleep tonight.
Oh, go ahead. Go ahead.
No, you sure you want to hear this?
Yeah, I'm up for it. Yeah, go for it.
You won't be able to sleep tonight. I'm promising you, okay? So you better drink a lot. I hope it's got a lot of alcohol.
Okay, I got more.
The issue is there was never a first human being in the universe. If we go back in time, 1,000,000 years, 1,000,000,000 years, 1,000,000,000,000 years, I don't care. You go back in time as far as you want. You will find another planet somewhere in the universe like the Earth where there was a human. And if you go 1,000,000,000 years before that, 1,000,000 years before that, 1,000,000,000 years before that, you'll find another planet in time there was a human. Yeah, and if you go further back in time, and since matter never came into being, there was never a first human.
Yeah, fair. That's probably true. I mean, that's certainly the kind of realization you come to when you're like on acid or tripped out or something, but you can't put it into words.
No, you can't. I think that blows your mind when you think that there was never a first human in the universe, right? In the universe. If you go back in time, and the reason we cannot contact another civilization, they will never contact us, is not only because, you know, life is a very scarce resource. There's relatively little carbon compared to silicon and other material that we have out there. You know, you need this CNOH, you know, carbon, nitrogen, oxygen, hydrogen to make a living entity. And what's the issue there? We have several issues. Let's assume there's another civilization, another human-like entity out there, right? The problem is not so much space, the fact that they could be very far away. The problem is time. We're staggered in time. In other words, we had electricity and communication, and maybe in the last 200 years, when we started playing around with electricity and trying to find out a little bit about it and sending microwaves and so on out there. But that's 200 years. That's a drop of water in the time of the universe. Yeah. And so you have another civilization, but they're maybe 200 years behind us or 200 years in front of us. They go extinct. We'll never hear about them. When we go extinct, the guys who come 200 years later, they're not going to hear about us. Yeah. You see the problem? So it's staggering in time, not only in space, but in time as well.
Okay, but you've heard of this idea that
civilization.
Yeah, so we're kind of getting a little bit off the point I was trying to make, but you've heard of the idea that if the universe, like there was a big bang and then there's inflation, and runaway inflation means that like you could have a bubble universe and then another bubble breaks off it and then a bubble breaks off that, and so
you believe in that? You believe in that, Chris? In that expansion in those universes?
No, I actually don't. But I'm just talking about the concepts behind it would be underpinned by certain ideas. So you can have like an infinite number of these universes, these bubble universes, and because it's an infinity, the number of molecules in each bubble can only be arranged in a certain number of ways, combinations, permutations, until you arrive at a direct copy of what was before. So in our universe now, we exist, we're talking to each other, and in this theory, there'll be a bubble some distance further away.
Have you ever done the calculation of that?
They did the calculation.
I mean, you're talking about almost impossibility. And to say it's a finite number, but I mean, to say that I'm going to appear in another gazillion years exactly the way I am now because the the pattern repeats itself. And so I'm going to show up a billion years later. Even if it were true, it's not going to be me. It's not going to be the same me.
Oh yeah, no, fair. But the point is that they'd be existing right now. They could be existing right now at the same time as us, because it would be just a direct copy of this universe, but just far away, but like in a different universe. But yeah,
assuming that were true, the question is, I mean, the possibility of there being trillions and trillions of universes already a far stretch of the imagination, and for there to be the same combination in which a pattern develops in a planet somewhere in another universe that is exactly like ours, or find another Bill Gates over there, you know, it's, man, the numbers are staggering. I mean, it's a nice story. It's nice as a novel, but to think that that's realistic, I don't know.
But yeah, I understand. But like, if you have an infinite number, then it kind of like, and as long as then
use the word infinite in my presence.
Right, but even you're talking about matter has always existed. So the point I'm making is that if we have the situation where matter always exists, and it's always recombining, and it's always going to make people, then there could be a time where we,
the statistics are against you. Let me say something else, Chris, that you might be interested in. Under the model, under the rope model, right? I'm saying there's all these atoms in the universe, right? And they're all interconnected. So if we had the eyes of God, or we could stand outside the universe somehow, right? And we could see our universe from far away, from a bird's eye perspective. You would see all these atoms, all these galaxies, all these stars, all these planets, right? You would see them from afar and say, that's our universe, okay? But what's the issue? The issue is all those atoms from that universe, right, are interconnected. That's our theory. That's our model, right? So they're all interconnected. All these atoms are interconnected. Now, there could be another parallel universe next to us in which none of those atoms are connected to any of our atoms. Now we can talk about two parallel universes. We share the same space, because space is nothing, but we don't share the same matter, in the sense that we're not connected to any of those atoms. So now you can talk about different universes, traveling from this universe, if you could, right, to that universe. So now you have two universes. How many of those could there be in the universe? Maybe there's not. Maybe there's only one. And if there is another one, well, yeah, you could speculate on anything. You can say there are millions or gazillions of them for all we know. But the issue is the following. We'll never know about that. That's good for speculation, but there's nothing you can do even. It's just for the imagination. It's just a ponder.
Yeah, but this wouldn't even require another universe. You just have our universe, and like it exists forever. So
I understand what you're saying. All I'm saying is statistics are against you.
Oh yeah, no, yeah, it's interesting.
No, how about symmetry? If you believe in symmetry, there could be a conjugate symmetry. You know, conjugate to human, conjugate our civilization. There could be another civilization which is a conjugate symmetry of ours. You know.
Yeah, but so again, the chance. I'm just saying that from a statistical point of view, it's unlikely, very unlikely. I mean, it's nice to ponder that, but I don't think we'll ever see anything like that. It's great for
gnosis like that. Nothing more. It could be all symmetrically.
Another kind of theory on how it could happen, because you're talking about even if it were to occur, it wouldn't be the same you. But then I've got this other kind of concept. Let's say
hopefully that guy has different atoms than me.
Yeah, but even so, but
it's like me, different atoms.
Look at it this way, Bill. Right? I would say that you believe, right? When you die, you just die. Like there's no soul, no eternal afterlife. It's just blackness or whatever.
It's just matter transforming itself. That's all it is.
Right. Okay. So, but think about it from your perspective as a subjective being. You have a point of view. Now, let's say that just goes black, or it's just nothing, right? But then, I'm just going to borrow something from physics, because that's where we're right. Okay. So, this concept of like you balance the pencil on its nib, and it's definitely going to fall. It's in an unstable position. They use it for the Higgs boson. They say it's at the top of the potential. Yeah. Right. So anything that's and then this idea that nothing is unstable. So if you were to be, you're this thing, let's say this confluence or something that that is capable of consciousness, at least now from an energetic level. And that disappears because you're dead, right? So, and then it's just nothing, right? And then that is unstable. And then, so even like given an infinite amount of time, it will just reappear and you'll be back. And we'll be having this conversation again, like given with a long enough timeline, it will just repeat and you will be the same person because it will be your consciousness redoing it. That's the theory I had years ago.
Let me address that because one of the things that the theory says is there's no such thing as time. Okay, why is there no such thing as time? And I invented a tool that people can use. I could put the graph there, but I think I can explain it. Imagine a movie of the universe. All the atoms, they're there in a single frame. Let's just cut one frame from the universal movie. There's all this motion going on in the universe, right? Let's just cut a single frame, okay? What do we see in that frame? Well, if we standing next to God, we would see all the atoms in the universe there in some form. Some of them have the form of you, others have the form of a star, others of a planet, and so on. All the atoms in the universe are in that single frame. That's it. There's no more atoms in the universe. That's all there is. Okay?
Yeah.
So each one has a certain distance from each other, and we call that location. The set of distances to this atom from all atoms in the universe, that's the location of this atom in the universe. Okay? So we say that the word existence, is an object, in this case an atom, that has location, that has distance to every atom in the universe. That's what we call by exist. That's the definition of existence. Physical presence, object that has location. Okay? So now we have that. Now what's the issue? On the next frame of the film, of the universal movie, right? Every atom there moved to a new location. Some nearby, some farther away, whatever. In the next frame of the film, you can cut that film as many chops as you want. It doesn't matter. But in the next frame of that film, as small as it is, every atom is in a different location. Just move somewhere else. Okay. When it moved, it's no longer in the previous frame. We understand that?
Yes.
So each frame is only location. It's only what we'll call the present, even though that's a bad word because present requires two frames. It's an interval of time. And we're not talking about time here. We're talking about not even motion. We're talking about location, distance, static concept. We're just saying that in this frame, everything had a given location. In the next frame, everything moved to a new location. Everybody occupies a different location. That means you cannot travel in time, back in time and kill your grandfather or shake hands with Julius Caesar. Why? Because all those atoms are no longer where they were then. They're all here. So if at the end of my nose, I have a hydrogen atom, right? That belonged to a dinosaur at the end of a dinosaur's nose. And I go back in time and meet that dinosaur and I'm face to face to him. That atom is in his nose and it's also in my nose. We got a problem. Yes. How can that atom be in two places at the same time? So I cannot go back in time because there's nothing to land on. There are no atoms there because all the atoms are in the present now.
Yeah, but there's another way of looking at it, Bill, because like if I say that, I die or whatever, and then so everything ceases to exist, but time and space for me also ceases to exist. So this idea that there's an infinite time.
Time and space. Wait a second. Hold on. I got to stop you there. Time and space do not exist because what does the word exist? An object that has location. Neither time nor space nor object.
I can come back on that because we're talking about a human subjective experience here, and we subjectively experience time and space. So if that experience ends, then it ends, and what's left is a possibility where I'm saying, okay, 1,000,000 years could elapse and then everything restarts. But because there's no time anymore, it could restart instantly. So there is no delay. So you could wind up in the afterlife straight away after you die, Bill. Be very careful.
Let me say something that is also concerning the theory, which gives you an idea here. These are all new points of view because of the rope model. No hydrogen in the atom in the universe. I'll just pick on the poor old hydrogen atom. No hydrogen atom in the universe is identical to any other hydrogen atom in the universe. I'll tell you why.
Okay.
They're exactly alike, but they don't have the same location.
Right.
They can never have the same location. Two hydrogen atoms, they cannot, they're equal in every sense, except that the ropes from this guy come from a little different angle than from that guy, and they cannot occupy the same location.
But they say that photons can occupy the same location, right? They say.
No. Remember, a photon under the rope model is a link of the rope. There's a photon. And either this one is not the same as this one. But they don't have the same location.
Threads can go through each other, Bill. Threads.
But it doesn't mean that you can say that they superimpose, okay?
Yeah.
But they come from different ropes. So in that sense, they're not the same. They're not the same link. That's true.
But Rajan is correct there in terms of like bosons can occupy the same space and still be different bosons. Two fermions.
Bozos are what you find in a circus. They're known as clowns. Bozo the clown.
Here's another issue. What you're talking about with the different frames of the film. It reminds me of Zeno's paradox. You know, where you can't nothing can actually move because if it did, it would have to.
It was Parmenides who came up with that, not Zeno. Zeno was part of the what is it? The Eloi. What's the name? There's a little town in Italy there, and they were the Eloi.
Zeno's paradox is movement, right?
Eloi school, and they were part of the same school. But the guy that came up with that was Parmenides.
Okay, but Zeno's paradox is.
No, I thought Zeno was Greek.
Yeah, they were both Greek, but they lived in Italy. It was a Greek colony in Italy.
Okay,
but Zeno's paradox is you move half the distance of the next one, and like that you never reach the end point.
Achilles never catches the turtle.
Right, but it doesn't. Is the idea it gets like so small that eventually it can't move or something?
Yeah, but that's math, and that's the kind of reasoning the mathematicians use. It's bullshit. I mean, of course Achilles is going to beat the turtle, but mathematically he proved that he can't. It's like we used to say in engineering, we used to say, hey, with statistics, you can prove that 100 elephants dance on a pin. And that's more or less what Zeno did there.
Yeah, it also reminds me, this idea.
Yeah, he always goes halfway. He never catches the turtle. But mathematically, that's correct. But physically, it's bullshit.
Right.
That's why you have calculus. That's why you have calculus, which proves that you can actually.
Right. And they had that kind of Parmenides also believed there was no motion in the universe. And Rene Descartes, he followed up on that, and other people as well. Even today, some people, because why? They say that there can be no movement because there's no such thing. Space, empty space, does not exist. That's what they said. Everything is filled. And so if everything is filled, as soon as you take something out, something fills that, which was Aristotle's point of view, that there is motion, but what happens is that, one thing comes out and the other thing occupies it instantly. So one guy concluded that there's no motion, and the other guy concluded, well, there is motion, but this is how we explain it. One thing, it's like the squares, the 16 squares, you move a square over, you leave a blank, and then another square moves in there, right? And what they were saying is the whole 16 squares are there, so you cannot even move. That's what Parmenides was saying, So
there has to be like a vacancy or something which allows that to move in, so the other thing can move in.
But space is that. Space is nothing. There is no such thing as space. Space is simply a background that we have of nothingness. What is nothingness? That which has no shape.
Yes,
then once we have a definition, we can talk intelligently about something and nothing. Nothing, that which has no shape. Something, that which has shape. Now we can talk intelligent. We have antonyms.
I kind of like that idea of there needing to be like this space so that something can move into it. It's kind of a fun concept. It's a little
hole, like a hole.
Yeah,
but
you have a hole where you can move.
You got to have your feet on the ground, Chris. You can't lose your feet off the ground.
Well, yeah, no, I've come up with similar ideas on things, but I haven't really, moved into them seriously or applied them seriously. Not that it matters or whatever, but
See, my theory starts from 0 point and micro black hole, from which I can construct everything else.
Yeah. Foundations are important. One of the biggest foundations are definitions. We need definitions. We don't have definitions out there. Everybody just glosses over and says, "Yeah, that looks good," and continues. And a lot of the arguments out there, a lot of the theories fall on definitions.
Yeah, I start from this and I go all the way up. The map, everything.
Yeah. You got to have a sound foundation like a building. You don't put good foundations, building comes down. Yeah. And that's what's happened with mathematical physics. You know, they don't have solid foundations because they don't have definitions. You ask them, what is energy? Oh, we don't know. Richard Feynman tells you he doesn't know what energy is.
Gravity?
Nobody knows what time is. What is time? Time is what a clock measures. What is that? I thought it was humans that measured. And then they tell you that it bends time. What do you mean you bend time, you warp time? Well, what is that? I mean, the language is wrong. The language is irrational.
See, one of the things I'm going to present probably whenever there is time, like in 10th of January, whenever I have some PowerPoint, I'm going to talk about two important things called perception and perspective. It's all in our mind. So perception is what you observe. Perception is perspective is like context or a setting. So suppose I'm seeing from a distance a point, right?
Yeah.
And then I see as a point. I don't see anything else, but I keep moving. I drive or I keep moving towards that. I see more and more features. I see a whole city, right? It's same as our star. From here, when you look at, we see a point, just a point, right? But when you go near, you are lost. Same way, you go away from Earth. Earth will be just a point.
Yeah, but Rajan, the problem with that is you're introducing an observer, a witness, and we that should not be the case. Existence has nothing to do with observation, with what you perceive. I mean, for all I know, you could be drunk. For all I know, you could be close or far away. Those are perspectives, but you know what exists there, independently of what you see or perceive. You know, that's different. That's what exists. So existence is separate from opinion.
Yeah, not opinion. In this case, for physics, you need some object, right? You need an object.
Yes, sir.
Okay, the object is from here, when we look at that object is a point, like a star.
Yeah, but again, the object is, whether it's a point or not, it's independent of your observation.
Yeah.
What you perceive a point, but you go up there and it's a planet, for example. So what you perceive is different than what actually is there.
Yeah. So, but the thing is that how do you, unless you perceive, unless you observe that, how do you know it is there?
You don't know. You make an assumption. In other words, look at God. God is a good example.
Yeah.
First, you have to determine whether God is a physical object or an abstract concept. I mean, what are we praying to? Love, intelligence, or are we praying to a guy with a magic wand who created the universe that looks like us? I mean, who are we praying to? Are we praying to an object or to a concept? Once you determine that, the question is, does he exist? Well, for this, you got to define the word exist. It's not a question of belief. If you believe in God, I don't believe in God. The other guy says, well, I don't know if God exists or not. Those are opinions. Existence should be independent of opinions. And so you have to define the word exist in such a way that you can use it consistently. And that's why I'm saying an object that has location, that's what we call existence. If God wants to exist, first, he's got to be an object. He can't be a concept. And second, he has to have location. There has to be a straight line of direction from the point of my nose to the point of his nose. If we have a straight line of direction, he exists by definition, not because I believe or stop believing.
But do you believe in God? Do you think
God it's the wrong question. It's an irrational question. You can't believe in existence. You're asking me, do I believe in the existence of a chair? And I'm saying, well, it's not a question of if I believe or not. If a chair is a physical object and it has location. It exists by definition, not because I believe in it.
Okay. About God. That's it.
Well,
God,
again, the
God
same
exists.
thing. First, you got to tell me what is God. Yeah, because I don't know what God is. I mean, is God a physical object or is it a concept? If it's a concept, I cannot believe in a concept. And if it's an object, it exists by definition, not because I believe. Imagine if poor old God exists. Let's assume God exists, right? And he's a physical object. He has location. But I don't believe in God. So he disappears?
No.
I can't make him disappear. If he exists, if he's a physical object, he has distance from my body, he exists by definition. And I'm saying, oh, but I don't believe in you, so you disappear. I don't believe in Rajan. And look, I stopped believing in Christopher and he disappeared. See how easy that was? Because I stopped believing in him.
See, how do you know that, like, we got off the air? How do you know the other person is existing? How do you know that?
How do I know that the person is what?
Suppose now we are here together, right? Suddenly we get off the air, we switch off, and then how do you know that you are in Chile still?
And again, knowledge is a question that really does not enter the world of science. We do not use knowledge. Knowledge is part of religion. Knowledge is religion because knowledge is defined. It's defined as justified true belief. Yeah. So it's a kind of belief where you believe more strongly. That's what knowledge is. I believe more strongly that Chris died. Yeah, that's my belief. I'm sure of it, but it turns out the next day
he comes back alive. He comes back alive. Resurrection. Yes. You are resurrected. Chris, you are resurrected.
Good time.
You believe in resurrection.
We just killed you, and I think you went to another universe and came back. See,
came back.
Yeah, it's very small.
His grandfather. He was his grandfather. Now his grandfather came, and then he became.
Okay, well that was good. Okay. Will we? I mean, we're like 3.5 hours, so we can.
A lot. Yeah.
We might as well call it a night there, and I'm gonna watch El Crazy Che.
Yeah, watch it. And, you'll have fun watching it.
I also will try to watch when I have time. And then we will see you. Chris will give you the link whenever you want.
Yeah. Anyways, I wrote there, Danny Vendramini. He's the guy who came up with the theory of them and us about Neanderthal. I wrote it there. You see his name? That's the guy that came up with that, with the Neanderthal with a big head.
Yes.
Okay.
Look him up. Danny Vendramini.
Oh no, yeah, I've looked into that theory. I say, I like it. You know, I think it's fun.
Well, what I like about Vendramini is at least I think it has a more rational explanation for how Neanderthal looked.
Okay.
Yeah. In other words, I think he looked more like a monster, a monkey, than what these guys. They put him as a Hollywood movie star. You see the last Neanderthal they made, he's all combed and so.
Yeah. Well, that's
Okay, guys, I gotta go.
Okay.
Yeah,
thank
great
you.
Talking to you,
Happy New Year again. And
we'll
catch up again. We'll catch up somewhere in January.
You gotta wait for me to get back to Germany.
Yeah. Okay. So have a bon voyage to Germany. So we'll talk